Hello friends, I welcome you to this episode of Learning Physics with IBM, and today I want to take you back to part 2 of magnetic fields and electromagnetic induction, where we are going to explore past paper questions and trying to solve them so that we gain confidence in dealing with past paper questions as far as magnetism is concerned. I hope you are going to enjoy this. And at this point, I just want us to move straight to our past paper document, that is electric fields, I mean magnetic fields and electromagnetic induction. I think we stopped on page, we must have stopped on page 189, and it's what we are going to search for here, page 189. My keyboard is not responding, so I will just scroll down. Page 189. Okay, so we stopped on page 188. I mean 189. So we were on this question here. We had finished the previous question. Page 189. So on page 189, a smaller coil of wire is insulated in a non-uniform magnetic field, as shown here. So you can look at the diagram. So we have a coil of wire which is treated in a non-uniform magnetic field, as shown here. So this is the coil. It has 40 turns. The coil consists of 40 turns of wire and moves with a constant speed in a straight line. The coil has as displacement x from a fixed point. The variation with x of the magnetic flux phi in the coil is given by this. So we are seeing how the magnetic flux is changing. And in this part it is decreasing from 5 to 3, then it increases from 3 to 7. That is the magnetic flux with distance x. The coil is moved at a constant speed between point P and the point where x is 3 centimeters. So between point P and the point where x is 3 centimeters, calculate the change in magnetic flux linkage of the coil. So when x is 0, the magnetic flux is 5 times 10 power negative 6. And when x is 3, of course, the magnetic flux we are seeing is actually 3 times 10 power negative 6 Weber. So we want to find the change in magnetic flux linkage. Of course, the change in magnetic flux linkage is just the product of the magnetic flux times the number of turns of the coil. So change in flux linkage, the change in flux linkage is simply going to be equal to the number of turns times the change in flux, which is the number of turns of the coil was 40, I think. The number of turns of the coil was 40, and the magnetic flux, so this is 40 times the change in the magnetic flux. It is changing from 5 up to 3, so that will be 5 minus 3, but it is times 10 power negative 6 times 10 power negative 6. So we press our calculator. From my calculator, this is giving me 8. This is giving me 8.0 times 10 power negative 5 Weber. So that is the change in the flux linkage, or the magnetic flux linkage. Then the EMF induced in the coil is 5.0 times 10 power negative 5 volts. Determine the speed of the coil. So if this is the EMF induced, we know that EMF is actually equal to the rate of change of a magnetic flux linkage. Therefore, since we want to find the speed, since the EMF is equal to the rate of change of magnetic flux linkage, which is going to be actually N times change in flux with the time. And also, we know that the speed, V, I will use V for speed, is equal to distance over time, and we want to find the speed. So I'm going to make T the subject here in this expression. If I make T the subject and I remove T in this expression, if I remove this T here, of course this is going to become the change in the change in the flux linkage. This will be the change in the flux linkage, which is this will be the change in the flux linkage, which is N times flux, change in flux, the rate of change of flux linkage. Instead of having delta T in the denominator, I'll just put there, I'm removing T. You notice that here T is going to be equal to X over V. So here when I put a substitute for T in the denominator, this will be over X, and this will be times the speed, which is V. And this means that if I try to substitute the quantities which have been given, then I'll be able to find the speed. Therefore, the EMF has been given as 5.0 times 10 power negative 4 to be equal to the flux linkage. We have got it as 8.0 times 10 power negative 5 times the speed, which I want to find. I will call it V. So this is times 10 power negative 5. Then why is this one going away? Okay, times 10 power negative 5 times the speed, which I'm going to call V. Then this is divided by the distance, the distance x, which is going to be actually 3. It is given in centimeters, so I'll change it to meters, so it will be 3 times 10 power negative 2. So making V the subject, I'll just press my calculator to make this V the subject. So 5 times 3 exponent negative 2 divided by 8.0 times 10 power negative 5. So this is giving me the speed, the final speed, as 0.19 meters per second as the final speed. 0.19 meters per second. On the figure 10.3, sketch the variation with x of the EMF E induced in the coil for values of x from x equals to 0 to x equals to 6.0 centimeters. So we just look at the graph. We want to sketch EMF. EMF is directly proportional to the rate of change of magnetic flux linkage. You notice that this will therefore be the same as, this will be therefore directly proportional to actually delta phi. From this expression, you see EMF is going to be equal to N delta phi over X, which is going to be directly proportional to the gradient. So we look for the gradient here. Since they have not given us a scale here, we shall just choose our own scale to represent these two values. So here the gradient is changing from, we have 5 minus 3 in the vertical over 3 in the x-axis. That is change in flux over the x-axis. This is actually 2 over 3. That is the gradient this side. Then the gradient the other side, we are having from, this is 7 minus 3 divided by, this is from 3 up to 6, which is actually 3. and this is 4 divided by 3. You notice that this gradient here is twice the first gradient. What does that mean? The EMF this side is going to be twice the EMF the other side. The EMF represented by this line here is going to be twice the EMF represented by this line from 5 to 3. And because these are straight lines, it means the gradient is constant for each of these lines. But this gradient to this side could be negative, yet the other gradient is positive. That means the EMFs are in opposite directions. So we now know the EMF on the left between 0 to 3, it could be, maybe if you want, you can make it to be negative, but constant because the gradient is constant. And the EMF the other side, you can make it to be positive and it is constant because the gradient is constant. But the EMF on the other side between 3 to 6 must be twice the EMF between 0 to 3. So when you are sketching the graph, you have to put that in mind. Okay, so the order of which one you make a negative doesn't matter, but let's maybe say, okay, negative gradient. The EMF is going to be, let's say it is represented by 5 small squares. I think these are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think they are about 15 small squares, so I will use only 5. So I will use 5 for the first EMF. 1, 2, 3, 4, 5. Well, let me use, okay, 5. I will use 5 for the first EMF and it will be a constant. I will draw a horizontal line here. Use a ruler and draw something very neat. I may increase slightly the thickness so that the line is visible. Draw a horizontal line along there. Then, of course, between 3 and 6, again, the EMF is in the opposite direction. So I'll put that one up, but we have seen the gradient was twice. So I'll count this because here I counted 5. Here I will count 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here I will count 10 and I will draw a horizontal line here. I'm just making it visible for you, just draw with a ruler. And this will be the graph we are looking for. This will be the graph. Alternatively, you could also draw the first part to be on the positive part, the other part to be on the negative part. There is no problem with that. Note that my lines may not be exactly along the grid lines, but yours should be along the grid lines because for you are using a ruler on a book or on a question on a paper. Okay, so note the EMFs are never zero. They're just switching from one value to another value, and they are becoming constant. Note that the EMF in the second part is twice the EMF in the first part because of the gradients. Also note that the EMFs are represented by horizontal lines because the gradients were constants for both parts of the graph. And I hope that one is understandable. Number six, define the Tesla. Define the Tesla, and this definition is 3 marks. I think it's one of the longest definitions in magnetic fields. We know that a Tesla is a unit of magnetic flux density. Therefore, a Tesla is going to be a unit of magnetic flux density. By the way, remember, the magnetic force was given by Bill. That means B is equal to F over I times L, and yet B is the one whose unit is the Tesla. So the Tesla is a unit of magnetic flux density, unit of magnetic flux density of a field normal, that is perpendicular to a straight long conductor. Why should it be long? To a straight long conductor or wire carrying a current of 1 ampere, and causing a force of 1 Newton, per meter of its length. Sorry for the space not being enough. Tesla is a unit of magnetic flux density of a field normal to a straight long conductor carrying a current of 1 ampere and causing a force of 1 Newton per meter of its length. In other words, we can define a 1 Tesla as being equal to 1 Newton per ampere per meter. That is a Tesla. But note that the current must be normal to the uniform magnetic field. That is the Tesla. The current must be normal to a uniform magnetic field. Because if the current is not normal to the magnetic field, this can be either sine theta or cos theta depending on the position of the angle. Okay. A charged particle of mass m and charge q is traveling with a velocity v in a vacuum. It enters a region of uniform magnetic field of flux density B as shown in the diagram here. The magnetic field is normal to the direction of motion of the particle. The path of the particle in the field is the arc of a circle of radius r. Explain why the path of the particle in the field is the arc of a circle. Explain why the path is the arc of a circle. So we have been explaining this for several times. We know that the force on the particle due to the magnetic field is always normal to the direction of motion, and this force is constant. So the magnetic force is constant. The magnetic force is constant and always normal. The magnetic force is constant and always normal or perpendicular to the direction of motion. To the direction of motion of the particle. Direction of motion of the particle. What does this mean? The speed of the particle remains constant, so the speed of the particle is constant. The speed of the particle is constant, therefore the magnetic force just provides the centripetal force. The magnetic force just provides the centripetal force. The magnetic force just provides the centripetal force. Show that the radius r is given by that expression. We have just seen that the magnetic force provides centripetal force. So if magnetic force provides centripetal force, then F due to the magnetic field should be equal to the force due to the centripetal force. So we have that BQV should be equal to mv squared over r, which means if I play around with the letters, one v has cancelled, making r the subject. R is going to be equal to mv divided by bq. So just equate bqv to mv, you see it is just one mark. So they just want this part BQV equals to mv squared over r. A uniform magnetic field is produced in the region PQRS as shown in the figure. The magnetic field is normal to the page. The magnetic field is normal to the page, either it is out or into the page. At point X, a gamma ray photon interaction causes two particles to be formed. The paths of these particles are shown in the figure 6.2 as we see. Suggest with a reason why each of the paths is a spiral rather than the arc of a circle. Why is each of the paths a spiral rather than the arc of a circle? Let's go back to the previous expression. We are seeing a spiral is showing that the radius is reducing, and we are seeing that radius times BQ is equal to m times v. So this is momentum. So, and we are seeing that the radius r is directly proportional to the momentum. So it could be the radius is decreasing, maybe because the momentum is decreasing. Of course, the mass of the particle may not be decreasing, but the speed could be decreasing. Therefore, the reason it could be the momentum or the speed is becoming smaller. So we can say the momentum or the speed of the particle, the momentum or the speed, the momentum or the speed of the particles is becoming smaller. So the radius also becomes smaller. Yeah, because the radius is directly proportional to speed or momentum. It could be that the momentum or the speed of the particles is the one becoming smaller, therefore the radius should be becoming smaller. State and explain what can be deduced from the paths about the charges of the two particles. We see that the paths are perfectly identical. Perhaps see that the paths are perfectly identical, and unfortunately they are in opposite directions. They are not on the same side. Perhaps the charges could be having opposite signs. So they said state and explain what can be deduced from the paths between the charges on the two particles. Charges. So we can think of them as having the same sign because one particle is moving this side and another particle is moving the other side. Perhaps they have opposite signs because in a magnetic field, charges with opposite signs move in different directions or in opposite directions. Therefore, we can say they're oppositely charged because the spirals are in opposite directions. So oppositely charged because the spirals are in opposite directions. Then state and explain what can be deduced from the paths about the initial speeds of the two particles. Initial speeds of the two particles. We notice that the initial radius, I think, from the initial distance from the point to the other end is approximately the same. The initial distance is the same. That means the initial radii is the same. So the initial radii are equal. Therefore, it means the initial speed, because radius is directly proportional to speed from this expression here. So we can say the initial radii, the initial speeds are the same. So we are saying initial radii from the diagram. We have seen the initial radii are the same. Radii, that is plural, double I, initial radii are equal. So this implies equal initial speeds. equal initial speeds. Okay. Positively charged particles are traveling in a vacuum through three narrow slits, S1, S2, and S3, as shown here. And each particle has a speed v and charge q. There is a uniform magnetic field of flux density B and a uniform electric field of field strength E in the region between the slits S2 and S3. So in S2 and S3 there is both electric and magnetic field. The electric field is downwards as shown by these arrows. State and the expression for the force acting on a charged particle due to the magnetic field. A charged particle due to the magnetic field. Of course, for a charged particle to experience a force, its velocity should have a component normal to the magnetic field. Therefore, we can write this as BV, BQV sine theta, or we can write BQV cos theta, depending on the angle. Then for an electric field, the force due to the electric field is given by Q times E, because they wanted it in terms of the quantities we have there. So that is BQV sine theta or BQV cos theta, depending on the position of the angle. And the other one is QE. Then the electric field acts downwards in the plane of the paper, as shown in the figure. State and explain the direction of the magnetic field so that the positively charged particles may pass through undeviated. So the electric field is downwards. Let's think of a positively charged particle entering in here. A positively charged particle entering here experiences a force in the opposite direction to the electric field. So the force due to the electric field on the positively charged particle is upwards. Meaning that for this particle not to be deviated, it should have a negative, it should have the force due to the magnetic field on it should be downwards. So we are saying the force due to the magnetic field should be downwards. And if the force due to the magnetic field is downwards and the particles are entering this direction, then by Fleming's left-hand rule, your thumb must point downwards and your second finger must point in this direction here where the particles are coming. In this direction here, the thumb is pointing downwards for the force on the particle. The second finger is pointing this direction. It means if you are holding your hand just above your paper on the table, you notice that the first finger is pointing upwards towards the roof. If you try to hold your hand with the elbow on the table, the thumb is pointing towards you, that is downwards. The second finger is pointing that direction, in the direction of the positively charged particles. The first finger is pointing to the roof, that is if you hold them at 90 degrees. The first finger is pointing to the roof, which means the force is actually, the field must be out of the paper. The field must be out of the paper. Okay. So the electric field acts downwards, meaning that the force on the positively charged particle. Oh, sorry. That is not true. Sorry. This is not true. I was considering a negatively charged particle. Okay, if the particle is positive or a positive particle moves in the same direction as the field, it is a negative particle which moves in the opposite direction. So the force due to the electric field must be downwards, not upwards. Sorry for that. That is just a slip of the head. The force due to the electric field is downwards. That means if the particles are to emerge without being deviated, the force due to the magnetic field should be upwards. So this should be upwards. The force due to the magnetic field should be upwards. So this now changes again. Hold your thumb pointing upwards. This is the direction of the thumb, because the thumb points in the direction of the force by Fleming's left-hand rule. This is the thumb. Then your second finger is going to continue pointing in the same direction. The second finger is in that direction. So with your thumb pointing upwards, up the page, and your second finger pointing in this direction, remember you are holding the fingers at 90 degrees. So it means your first finger must be pointing onto the table where your paper is. So that means the field is into the paper, not out of the paper. Sorry for that. So the force due to the magnetic field must be upwards to balance the force due to the electric field, which is downwards. So FB must be opposite. FB must opposite in direction. FB must be opposite in direction to FE. Remember, F is going to be the electric force. Okay. So by Fleming's left-hand rule, left-hand rule, the field must be into the plane of the paper. So note here very carefully. Because the field is downwards, a positively charged particle experiences the force in the same direction as the field. It is the negatively charged particle which experiences a force in the opposite direction to the field. It is the negatively charged particle which experiences a force in the opposite direction to the field. If the field is downwards, then the force to the electric field on the positively charged particle is also downwards. To balance this force, the force to the magnetic field must be upwards. And therefore, since we know the direction of the particle, this is the direction of the particle, this is the direction of the second finger, and this is the direction of the thumb. When you hold them at 90 degrees with the second finger pointing in this direction, on your just above your paper, the thumb pointing upwards, it means you rotate your hand. If the first finger is pointing away from you, you rotate your hand so that it points to the table. For this combination to come out very carefully. That is why we are saying FB must be opposite in direction to FE, so that um, so that so that the field will be out of the page. Maybe I have the hand here. I can try to search for it so that I can demonstrate Fleming's left-hand rule. Sorry, this one is not working. Okay, a bar magnet is suspended vertically through the field. A bar magnet is suspended vertically from the free end of a helical spring as shown in here. So the magnet is suspended as shown here. One pole of the magnet is situated in a coil. The coil is connected in series with a high resistance voltmeter. High resistance voltmeter. It could be of infinite resistance. The magnet is displaced vertically and then released. The variation with the time t of the reading V of the voltmeter is shown here. Okay, so we see V is constant throughout with the time. The first question is telling us to state Faraday's law. You shall state this several times until we are confident with it. So Faraday's law, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. When we talk about magnetic rate of change of magnetic flux linkage, we are also referring to the rate of flux cutting. So I can also say directly proportional to the rate of flux cutting. That is Faraday's law. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Use Faraday's law to explain why there is a reading on the voltmeter. One pole of the magnet is situated in a coil. The coil is connected in a series with a high resistance voltmeter. The magnitude is displaced vertically and then released. So we see that the reading varies from 0 to maximum, changes direction, and so on and so forth. Of course, we have seen Faraday's law. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. That means that whenever there is a change in flux linking or the rate of flux cutting is changing, it means there will be an EMF induced. So explain why there is a reading on the voltmeter. So the moving magnet is therefore causing change of flux linkage, as simple as that. The moving magnet causes change of flux linkage. In other words, when the magnet moves between inside the coil, the turns of the coil cut the magnetic flux or the magnetic field of the magnet, and EMF is induced in accordance to Faraday's law. Use Faraday's law again to explain why this reading varies in magnitude. We see that it varies in magnitude from 0 to maximum. And why is it varying in magnitude? Of course, the rate of cutting is what determines the magnitude. And it could be that the rate of cutting is varying. And why is it varying? Perhaps the speed of the magnet is varying. So we shall say the speed of the magnet varies when it is moving in the in the coil. So the speed of the magnet, the speed of movement of the magnet varies. The speed of movement of the magnet varies, so varying the rate of change of flux linkage. So this is varying the rate of change or varying the rate of cutting, varying the rate of change of flux linkage. Or varying the rate of cutting. That's why the magnitude is changing, because in accordance to Faraday's law, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Okay, part 3. Part 3. The reading has both positive and negative values. You see we have positive value of V and negative value of V. Perhaps as the magnet is moving, it keeps changing direction, going down, going up, and so on and so forth. So it means the EMF must also change in size or in polarity. Or the cutting changes direction. Sometimes it's cutting downwards, sometimes it's cutting upwards. So we shall say the magnet changes direction of motion. The magnet changes direction of motion, so also changes the current or the EMF also changes the what? The direction. So the current also changes direction. Because the magnet changes direction of motion, the current or even the EMF also changes direction. Use the figure 5.2 to determine the frequency F naught of the oscillations of the magnet. So we know frequency is going to be related to the period. Frequency is equal to 1 over T. Let's just find the period from here up to here. That is one cycle. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is at the center of 0.5 and 1.5. I think this is 0.75. So the frequency is going to be 1 over 0.75. So frequency is 1 over period, which is going to be 1 over 0.75 seconds, because the period is 0.75 seconds. And when I press my calculator, this is going to be 1.33 hertz. 1.33 hertz. The magnet is now brought to rest, and the voltmeter is replaced by a variable frequency alternating current supply that produces a constant root mean square current in the coil. The frequency of the supply is gradually increased from 0.7 to 1.3 F naught, where F naught is the frequency calculated in B. On the axis, sketch a graph to show the variation with the frequency F of the amplitude A of the new oscillations of the bar magnet. So now the magnet is being brought to rest, and the voltmeter is being replaced by a variable frequency alternating current supply that produces a constant root mean square current in the coil. The frequency of the supply is gradually increased. So we are increasing the frequency of the supply so that, of course, there is the oscillations of the magnet are going to be damped due to the magnetic field, which is caused by the constant voltage, the constant supply here. The constant supply is applied here, which is alternating, which is going to create a magnetic field that opposes that of the magnet. In other words, the magnet is going to be damped. The oscillations are going to be damped. So that one you have it in mind. So part 1 says, name the phenomenon illustrated on your completed graph. Or part 1 says, on the axis, sketch a graph to show the variation with the frequency F of the amplitude. So this is damping, of course. When the frequency of the SC, which has been supplied, balances with the natural frequency of the magnet, Remember, F naught is the frequency that we have calculated above, that is 1.33, which is the natural frequency of the magnet. When that frequency is matched with the frequency of the current, because it is gradually increased, resonance occurs. Therefore, at that point, the magnet is supposed to oscillate with the maximum amplitude. But then, if we exceed that frequency, then remember, when the frequency exceeds or is less than the natural frequency, then the amplitude decreases. Therefore, our graph will just be something like this. With a peak, if you remember from simple harmonic motion, when resonance occurs, the amplitude is going to be maximum when the driving frequency F matches with the natural frequency of the magnet. So resonance is occurring here, but there's a possibility of the system being damped in accordance to Lenz's law. So the curve will be like that. That is the resonance curve. Name the phenomenon. This is automatical resonance. That is automatical resonance. So there is some damping. That's why you see it is not a very sharp peak. That means there is some damping. If there was no damping, I would draw a straight line, just a straight line like a letter V. State one situation where the phenomenon named in Roman 1 is useful. Where is resonance useful? Resonance is very useful. For example, quasicrystals. In quasicrystals, are used for timing. They use resonance, timing, controlling clocks and watches. Quasicrystals are also used for producing ultrasound. Production of ultrasound. So in the production of ultrasound, the quasicrystals are also used there. We shall see that in medical physics, where we shall see quasicrystal placed in the piezoelectric transducer to produce ultrasound when an alternating voltage is applied across it. Okay. Next, state what is meant by a magnetic field. A magnetic field is a region of space where a particle which is moving, a moving charged particle, where the poles of a magnet or the magnetic material, where a current carrying conductor creates or experiences a force. So that is a region of space where a force, where there is a force, let me just say where there is a force. Region of space where there is a force. There is a force on, or I will say produced by a magnet. It can be on or by or produced by. So I will say there is a force on or produced by. Then I will say a magnetic pole. For you can state one in an exam. You can say by or on a magnetic pole. It can be on or by a current carrying wire or current carrying conductor. Or it can be on or by a moving charge. It must be moving. On or by a moving charge. It can be on or by a moving charge. So that is the magnetic field. A region of space where there is a force on a moving charge. A region of space where if there is a force produced by a moving charge. A region of space where there is a force on a magnetic pole, or a region of space where there is a force produced by a magnetic pole, and so on and so forth. A charged particle of mass m and charge q is traveling with a velocity v in a vacuum. It enters a region of uniform magnetic field of flux density B as shown here. So we have a region of uniform magnetic field, flux density B. So the magnetic field is normal to the direction of motion of the particle. The path of the particle in the field is the arc of a circle of radius r. Explain why the path of the particle in the field is the arc of the circle. So now we know that the magnetic force is constant. The magnetic force on the particle is always constant and normal too. So the magnetic force the magnetic force the magnetic force on the particle is constant. The magnetic force on the particle is constant and always normal to the direction of travel. So the speed of the particle is constant, doesn't change. The speed of the particle is constant, so the magnetic force just provides centripetal force. So the magnetic force just provides centripetal force. The magnetic force just provides the centripetal force. Show that the radius r of the given is given by that expression. We have seen this question earlier on. Since the magnetic force Fb is providing the centripetal force, so I'll just say magnetic force Fb provides the centripetal force. I'll just write Fc. So I'll say that mv squared over r is equal to b qv. And when you cancel out one v, you notice that r will be equal to mv divided by bq. A thin metal foil is placed in the magnetic field in B. A second charged particle enters the region of the magnetic field. It loses kinetic energy as it passes through the foil. The particle follows the path shown in the figure. It loses kinetic energy, remember. On the figure, mark with an arrow the direction of travel of the particle. They said it loses kinetic energy. If it loses kinetic energy, then the particle must be moving in this direction. Because the upper part, the path is closer to the foil. The bottom part, the path is farther away from the foil. That means because they say the second charged particle enters the region of the magnetic field, it loses kinetic energy as it passes through the foil. You notice that here, before it passes through the foil, this part here is larger, but as it passes through the foil, you see the path is closer to the foil. That means it's losing kinetic energy. Therefore, the arrows should be pointing from the bottom to the top. So the path is that one as required by the question. Here I'm just saying the path is that because if the kinetic energy is reduced, it means the speed is decreased. It means the path should be closer to the aluminum foil as it passes through. Yet in this part, if I was to put the arrows pointing downwards, the path will be away from the foil, which would mean the kinetic energy is actually increasing as it passes through the aluminium foil, yet it is supposed to be decreasing. Okay. The path of the particle has different radii on each side of the foil. The radii are 7.4 and 5.7 centimeters. Determine the ratio final momentum of the particle over initial momentum of the particle. We have seen that R was equal to mv divided by bq. R was mv divided by bq, and this meant that momentum, because mv is momentum, so momentum is equal to rbq. It is entering the same magnetic field, so this is going to be B and Q are the same. What is changing is the radii. So we want the final momentum of the particle over the initial momentum of the particle. We want the ratio. So this is going to be the final radii, which is 5.6, because the radius, this part is going to be 7.4, and the radius of the other part is going to be 5.7. So the final and the momentum is directly proportional to the radii. So this is going to be 5.7 divided by 7.4, and the ratio is going to be 0.77. So the ratio is going to be equal to, the ratio is the final radius, R final, because BQ are the same, over R initial, because BQ is the same. These ones cancel. This is 5.7 over 7.4, which is 0.77. That is the ratio. Then a proton of mass m and charge q is traveling through a vacuum in a straight line with a speed v. It is a proton, so it is positively charged. It enters a region of uniform magnetic field of magnetic flux density B, as shown in the figure. The magnetic field is normal to the direction of motion of the proton. Explain why the path of the proton in the magnetic field is an arc of a circle. We shall not get tired of that question. So they have already told us that the magnetic force, the magnetic field is normal to the direction of motion of the particle. And we know that the magnetic force is constant and always normal to the direction of, or to the direction of motion of the particle. So we are saying the magnetic force on the proton is constant and always normal to the direction of motion. The magnetic force is also constant and always normal to the direction of motion of the particle. Therefore the speed remains constant. The speed is constant. The speed is constant, and thus the magnetic force just provides the centripetal force. The magnetic force just provides the centripetal force. So the magnetic force just provides the centripetal force. This is the word. This word is provides. I know some of us, we are not good at spellings. The magnetic force just provides centripetal force. This is a common equation, and by now you should be familiar with it. The magnetic force is always constant and always normal to the direction of motion. When we say the direction of motion, it is equivalent to saying to the velocity. So it is always normal and it is constant and always normal to the direction of the velocity or the direction of motion. So the speed does not change, but the velocity is changing because of the direction, and the force is always normal to the direction. Thus, the magnetic force just provides centripetal force, which makes the particle to move in a circular path. The angular speed of the proton is in the magnetic field is given as omega. Derive an expression for omega in terms of B, Q, and M. So we have seen that the magnetic force provides centripetal force. Therefore, and we know that the magnetic force, we have seen that the magnetic force provides the centripetal force. And we know that the magnetic force is B, Q, V. And this is providing the centripetal force, which is mv squared over r. We also know that V is equal to omega r, and V is equal to omega times r. So I'm now substituting. So one V has already cancelled. I have that BQ is equal to M, where there is V, I will put omega r, and this is divided by r. And when you open one r, the r has cancelled. Or maybe this is not very visible. I've replaced V with omega r. So r has cancelled. This r cancels with that one. So you remain with the BQ equaling to M times omega. So therefore we can simply say that omega is equal to BQ divided by M as required. So we must have looked at this. First of all, the magnetic force is providing a centripetal force. Second, we equated this and we know that V is omega r. Then we simply do the algebra and arrive at omega equaling to B Q over M. State the relation between the magnetic flux density B and the magnetic flux phi. B and phi, explaining any other symbols you use. So B and phi have been defined. So we know that the magnetic flux phi is given by BA sine theta, or it can be A cos theta, but I will use sine theta this time, where I will say A is the area. This is the area through which the flux passes, area through which the flux passes. A is the area through which the flux passes, and theta is the angle between B and the plane of area. Alternatively, I would just have said flux is equal to B times A. And here, because B has been defined, I will just define A. I just define A as the area normal to the field. A is the area normal to B. So I would just state this statement here as simple as that. Flux is equal to BA, where A is the area normal to the field or normal to B. That would be as simple as that. But when I define it like this, I must define area. A is the area through which the flux passes, and theta is the angle between B and the plane of the area. Okay. Next, a large horseshoe magnet has a uniform magnetic field. Has a uniform magnetic field between its poles. The magnetic field is zero outside the space between the poles. A small hollow probe is moved at a constant speed along xy. That is midway between between and parallel to the faces of the poles of the magnet as shown here. An EMF is produced by a hollow probe when it is in the magnetic field. So EMF is when it is in the field. The angle between the plane of the probe and the direction of the magnetic field is not varied. Let's say it is maximum. It is maybe 90 degrees because, okay, because it is moving parallel to the faces, then maybe the plane and the magnetic field is 90 degrees. The angle between them is 90 degrees. On the axis of the figure, sketch a graph to show the variation with the time t of the EMF VH produced by the Hall probe. So we know that VH, the Hall voltage, is equal to BI divided by NTQ. NTQ and I are going to be the same. So what is going to be changing is the magnetic field. So we know that VH is directly proportional to B, and B is depending on the angle. B depends on the angle between the plane of the Hall probe and the magnetic field. If the angle is not varied, then it means wherever the Hall probe is in the magnetic field, there's an almost constant VH. Excuse me. So whenever the Hall probe is in the magnetic field, there's a constant value of VH because the angle is not changing, meaning B is not changing. Nothing else is changing, but only that the Hall probe is moving into the field and out of the field. Whenever it is out of the field, B is 0. So outside the field, I will draw a horizontal line. Why can't I find that ruler? I will increase the thickness to make my line visible. So here they said the probe enters. Here the probe enters the magnetic field. Here the probe leaves. So when it has left, when it is before it enters, there is no magnetic field. So VH is 0. So I'll draw a horizontal line here outside. And when it has left, it is also going to be 0. So I'll draw a horizontal line here. But there is that small interval between entering, when it is just entering, where the voltage, where the voltage rapidly goes to a certain value, and when it is just leaving, where the voltage rapidly goes to a certain value. Inside the magnetic field, the voltage is constant because the magnetic field is not changing. So inside, I'll draw a horizontal line not at 0 because it is a magnetic field, so VH is constant and is not 0. So I'll draw a horizontal line inside. But there's this small interval between changing at this point when it is just entering and the other point when it is just leaving. So here it is rapidly raising to a certain value, and here it is rapidly going to be going to a certain value when it is moving outwards. So I'll draw a line here. It is not very horizontal. I don't want it to be very, very sharp, but it is supposed to be a sharp decrease. There's a sharp increase and a sharp decrease at the ends. So here I will draw slightly a line like this. A sharp decrease and a sharp increase. There's a sharp decrease and a sharp increase. I think I didn't draw this very well. It is not very sharp. Normally, before you write in your document, it's better you wait when I'm done with the question, because I'm a human being, I make errors, and sometimes I may want to correct my errors. So this is actually the graph we are supposed to be drawing. Note that when inside the field, VH is directly proportional to B, and VH is going to be a constant because the field inside is constant, is uniform, it is not changing. And as we move out of the field, VH is going to be 0. So that will be our graph. VH is 0 outside, VH is constant inside. There's a sharp increase when you're entering the magnetic field and a sharp decrease when you're moving out of the magnetic field. So you have such a graph. Okay, state Faraday's law again. We should not get tired of stating this. The more we state it, the more we become familiar with it. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. The hollow probe in B that we have seen is now replaced by a small flat coil of wire. The coil is moved at a constant speed along the line XY. The coil is moved at a constant speed along the line XY. The plane of the coil is parallel to the faces of the poles of the magnet. So we are moving a hollow probe and we are putting a coil whose plane is parallel to the poles of the magnet. The plane of the coil is parallel to the faces of the poles of the magnet. On the axis of the figure, sketch a graph to show the variation with time t of the EMF induced in the coil. So we have seen we can even just get the EMF from the VH. An EMF is induced when there is a change in magnetic flux linkage. We are just replacing the hollow probe with a coil, and we are seeing between 0 to entering the magnetic field. Of course, there is no magnetic field. When there is no magnetic field, there is no induced current. Therefore, there is no EMF. So it means before entering, still the graph will be along the x-axis, because E is directly proportional to the rate of change of magnetic flux linkage. If there is no VH, if VH is 0, B is 0. When B is 0, because E is equal to N times the rate of change of flux with time, which is the same as NBA over time. Outside B is 0, so it means outside E is also 0. So outside, I will increase the thickness. This time I'm using some kind of ruler to draw a nice line. So outside, there is going to be a horizontal line along the x-axis because B is 0. I don't want that line to reach on that vertical one. Outside, there will be a horizontal line that is going to be 0. Then inside, again, B is constant. When B is constant, the rate of change, the flux linkage is constant. That means there is still no induced EMF when the flux linkage is constant. It must be changing. So still inside, I will draw another horizontal line inside. So there will be another horizontal line inside because the flux, the B is constant inside. When you are in the magnetic field, B is constant. It must be changing. Outside B is 0. So outside, I will write this in, let me write this here. Outside B is equal to 0. Obviously, E is going to be 0. Then inside B is constant, it is not changing. And if B is not changing, yet the area is not changing, the number of turns is not changing, then if B is constant, again, E is also going to be 0. But there is that small interval when there is a change rapidly from 0 to maximum in the magnetic field when you are just entering and when you are just leaving. At those points, the EMF moves to actually the EMF goes to a rapid high value at entering and it goes to a rapid high value at moving out. So we shall have short pulses. We shall have short pulses at those points. So we shall have short pulses, and these short pulses are going to be in opposite direction because you are entering, that is in one direction, and you are leaving the magnetic field, that is in the opposite direction. Therefore, we shall have short pulses somewhere here. So we shall have short pulses at entering. They are very short. They are not very large. So we shall have short pulses there. And we shall have short pulse here. These are, of course, going to be equal in magnitude and in opposite direction. So that is what we are talking about here. Short, very short pulses at entry and leaving. Short pulses at the point of entering the magnetic field and at the point of leaving the magnetic field. Because they must be in opposite direction, because entering, that is the field is in one direction, is cut in one direction, and leaving the field is cut in opposite direction. That is very, very important. Okay, so this is the graph. This is the graph. I think this is normal around 3 to 4 marks. And if this is being marked, this is very important. Short pulses in opposite direction and having horizontal lines along the x-axis indicates that the student understood the concept here of EMF, of induced EMF. Okay. State the condition for a charged particle to experience a force in a magnetic field. Of course, for a charged particle to experience a force in a magnetic field, it must be moving, not necessarily moving parallel to the magnetic field. It must be moving with its velocity, having a component normal to the magnetic field. So the particle must be moving. The particle must be moving. The particle must be moving with a component, of its velocity normal to the magnetic field. Even if it moves, but when it is moving parallel to the magnetic field, it will not experience a force. State an expression for the magnetic force F acting on a charged particle in a magnetic field of flux density B. Explain any other symbols you use. Okay. So we want the expression of the magnetic force on a charged particle. They have given us F, B, and yeah, of course, the other symbols we shall explain them. So F, of course, we shall simply say F is equal to B Q V sine theta. If you don't include sine theta, then you must define clearly what V is or B is. So since F and B were given, we shall only define Q, which is the charge of the particle. We shall define V, which is the speed of the particle. And we shall define theta, which is the angle between the direction of the particle and the field. It's the angle between the direction of the particle and the field. That is BQV sine theta. It could also be BQV cos theta. But when we use cos theta, then it will be the angle between the direction of the field and the normal to the direction of the particle. That is theta. A sample of a conductor with rectangular faces is situated in a magnetic field as shown here. Okay. The magnetic field is normal to the face A, B, C, D in the downwards direction. Electrons enter faces C, D, H, G at right angles to the face. So electrons are entering from the other side, from this side. As the electrons pass through the conductor, they experience a force due to the magnetic field. Yes, they should, because they are moving normal to the magnetic field. On the figure 6.1, shade the face to which the electrons tend to move as a result of this force. So here we are pulling out Fleming's left-hand rule. You are going to reverse the second finger to point in the opposite direction to that of motion of the electrons. You make the first finger point downwards onto your page. You lift your page vertically so that the page is facing you directly, just vertical. Hold your page vertical, like I'm holding my computer vertical, and the first finger is pointing downwards along the field, or down because the field is downwards. Hold your page vertical. Let it stand, make it vertical, facing you. The plane of the page is just vertical, it's facing you. The first finger should point downwards. Reverse the second finger to point in the opposite direction to the direction of motion of the electrons. And when you do that with the first finger pointing downwards, it points to the table. When you reverse the second finger to point in the opposite direction to that of the electrons, you notice that the thumb is pointing towards BFCG. The thumb is pointing towards BCGF. Therefore, it means the electrons are actually being pushed towards the other end. Using Fleming's left-hand rule for electrons, we reverse the second finger to point in the opposite direction to that in which they are moving. Alternatively, you can use the Fleming's right-hand rule. When you use Fleming's right-hand rule, you don't reverse the second finger. Using Fleming's right-hand rule, again, hold your page vertical. Let it be vertical on your table. We are just proving with the right-hand rule. The first finger is pointing downwards. The second finger of the right hand is going to point in the same direction as that of the electrons. And still you see the thumb points towards BCGF. So it means we shade BCGF. Normally, I discourage you to use Fleming's right-hand rule for the direction of force on charged particles, because in explanation you will not always refer to Fleming's right-hand rule. You will always refer to Fleming's left-hand rule. We normally prefer to use the right-hand rule when we are finding induced current. Okay, so we have shaded BCGF. Part 2, the movement of the electrons in the magnetic field causes a potential difference between two faces of the conductor. Using the lettering from the figure, state the faces between which the potential difference will occur. State the faces between which the potential difference will occur. So obviously, when the electrons are moving like that, the electrons are experiencing a force towards BCGF. That means the positive ions are experiencing a force between ADHF. That means the PD is going to occur between ADHF and BCGF. I mean ADHE and BCDF. So that is the faces they are talking about here are B, C, GF, and ADHE. Explain why the potential difference in B causes an additional force on the moving electrons in the conductor. So initially, the electrons are experiencing a force only due to the magnetic field. But when this side becomes positive with positive ions, and the other side is negative with negative ions, then there is a potential difference between this end here and the other end. So a potential difference causes an electric field. That means a charged particle in here, say an electron, is now experiencing two forces. One is due to the magnetic force pushing it to BCGF, and two is due to the electric force which is pushing it due to ADHE. When the two forces balance, then the electron cannot move on any side. Therefore, the PD which we have talked about there gives rise to an electric field. So the potential difference, the PD gives rise to an electric field. The PD gives rise to an electric field, and the electric field gives rise to a force. The electric field gives rise to a force, the electric field gives rise to force on an electron, and this force is equal to Q times E. So the force due to electric field is Q times E. So the electric field gives rise to a force on an electron, which force is given by charge times E. Okay. State Lenz's law, remember, as Faraday was concerned with the magnitude or the size of the induced EMF, Lenz was concerned with the direction. So the direction of the induced EMF is always such as to cause effects that oppose the change producing it. The direction of induced EMF. Direction of induced EMF is such as to cause effects that oppose the change producing it. Direction of induced EMF is such as to cause effects that oppose the change producing it. Number next. Okay, so this one is just typing error. Two long straight parallel conductors, two long straight parallel copper wires A and B are clamped vertically. The wires pass through holes in a horizontal sheet of card PQRS as shown here. Okay. There is a current in wire A. As you can see shown by the arrow. On the figure, draw four field lines in plane PQRS to represent the magnetic field of the current in wire A. So you see that the current is coming out of the page using the right-hand grip rule. Grip the pen in your hand, your right hand, with the thumb pointing upwards, because the current is coming out of the page. You notice that the remaining four fingers are folding anti-clockwise. The remaining four fingers, when you grip your pen in your hand, your right hand, with the thumb pointing upwards, the remaining four fingers are folding anti-clockwise. That means the field around this wire is anti-clockwise because the current is out of the page. So they are going to be concentric circles as we learned in class. So these are concentric circles, but remember, as you move away from the wire, the field strength reduces. Use a compass to draw very neat concentric circles. So you will draw concentric circles around the wire, and these are going to increase in separation as you move away from the wire. So concentric circles around the wire. Me, I don't have a compass, so I will draw with a free hand. But at least my separation of the field lines will be increasing as I move away from the wire. So even yours should increase as you move away from the wire. So when you use a compass, you can easily estimate the diameters very, very fast, very easy, the radius very easy. So the arrows are going to point in this direction here. Using the right hand grip rule, the arrows point in that direction. When you use a compass, you adjust to get so that the separation is increasing away from the wire very easily and neatly. So you should put that into your mind. concentric circles whose separation increases with distance from the wire, and they should be in an anti-clockwise direction. Then wire A also experiences a force. State and explain which wire, if any, will experience the larger force. They have not given us the direction wire B, but of course, wire A also experiences a force. State the direction which wire, if any, will experience a larger force. They say the current in wire B is larger than the current in wire A. A direct current is now passed through wire B in the same direction as wire A. So the current is in the same direction. I had skipped that question. On the figure 7.1, label an arrow in the plane to show the direction of the force. Of course, when current is in the same direction, the force is attractive, so the arrow is supposed to point in that direction. So this is the arrow here. The arrow is supposed to point in that direction because when wires carry current in the same direction, the force is attractive. So the force on wire B is towards wire A. Wire A also experiences force. State and explain which wire, if any, will experience the larger force. Of course, we saw that by Newton's third law, the forces are equal but just opposite. Alternatively, the force on each wire is directly proportional to the product of the two currents or both currents in the wires, so the forces are equal. So the force on each wire is proportional or depends on the product. The force on each wire is proportional to the product of the two currents. The product of the two currents, so the forces are equal. Alternatively, you could talk about Newton's third law. So by Newton's third law, I'll just write, okay, by Newton's third law, the forces are equal but opposite. Forces are equal but in opposite direction. In opposite directions. So the forces are the same. Whether the current is in the same direction or in the opposite direction, the forces are equal in magnitude because the force on each depends on the product of the currents. And the product of the two currents, whether one is large and another one is small, the product is always the same. The force is directly proportional to the product of the currents. So whether I2 is bigger than I1 or I1 is bigger than I2, the force on each is depending on that product. Okay. The currents in wires A and B are now replaced by sinusoidal AC of equal peak values. The currents are in phase. That means they always change direction at the same time. Describe the variation, if any, of the force experienced by wire B. So it means the force experienced by wire B will always be towards A because the currents in both wires are changing direction at the same time since they're in phase. So it means the force is always attractive. Therefore, the force on wire B will always be towards wire A, since the currents will always be in the same direction. But it is alternating current. What does that mean? It is alternating current. That means the force is going to be varying from 0 to maximum because it's alternating current. We know that for alternating current, it grows from 0 to maximum, changes direction, or decreases to 0 and then changes direction. But since the force is depending on the product of the currents, it means the force will never cross to the negative part. So it will just vary from 0 to a maximum value. And therefore, since for alternating current, for both currents, I is going to be equal to I naught, sine omega t. When I multiply I1 and I2, I naught will always be positive. Sine omega t will also be a positive because it will be squared. It will be squared. So if the currents are the same, let's say I1 and times I2 will be I naught squared sine squared omega t. I naught squared will always be positive. Sine squared omega t will always be positive. That means the force will never go below the force will not be a negative. It will not change direction. It will not be a negative. So we are saying the force is always towards. The force is always towards wire A. We have seen why they say they are in phase. The currents are in phase. That means they are always pointing the same direction. Whether they are all pointing downwards or they are all pointing upwards. That means the force between the two wires is always attractive. So the force is always towards wire A, but it varies, and it varies from 0 to maximum, 0 to a maximum value. It varies from 0 to a maximum value. Note that the force is directly proportional to the product of the currents. The force is depending on the product of the current, and the product of the current will always be positive, but it varies from 0 to a maximum positive value. So the force also varies from 0 to a maximum value, and the variation is sinusoidal. The variation is sinusoidal. The variation is because it is sine squared, it is sinusoidal. In other words, it is depending on sine squared. But this will happen at a frequency which is going to be twice the frequency of the current. Since it is not changing direction, then to be at twice the frequency of the current. The force is always towards wire A and varies from 0 to a maximum value. The variation is sinusoidal at twice the frequency of the current. Because it is not changing direction, it will vary at a frequency twice that of the current. Okay. A person is to be investigated using MRI. Although MRI scanner was removed from the syllabus, that's why you see part A is missing. So we shall just concentrate on the parts which are relating to what we are still studying. The frequency f of the electromagnetic waves emitted by protons are on relaxation in an MR scanner is given by F is equal to CB. B is the total magnetic flux density and C is a constant equal to 1.34 times 10 power negative 8 per second per Tesla. The magnetic flux density B is given as that 2.0 times 10 power negative 4 Teslas for each 1.0 centimeter thickness of tissue in a section. The scan is adjusted so that the thickness of each section is 3 millimeters. Calculate for corresponding points in neighboring sections the difference in magnetic flux density. So we want difference in magnetic flux density, difference in flux, difference in flux density. So they have told us that for each 1 centimeter thickness of tissue, the magnetic flux density changes by that. Now the scan is adjusted so that the thickness of each section is 3.0 millimeters. So it is 3.0 millimeters. So if for 1 centimeter the change is that, how about for 3.0 millimeters? So we want to remember we want the answer in Teslas. So for 1 centimeter, it is going to be that. So how about for 1 meter? Note that 1 meter is equal to 100 centimeters. So it means for 1 centimeter, for 1 meter, the thickness is going to be equal to actually 2.0 times 10 power negative 4, then times 100, because 1 meter is 100 centimeters. So for 1 meter, it is going to be 2.0 times 10 power negative 2. It becomes negative 2 because this was per centimeter, now this is per meter. So it becomes negative 2. Then times our thickness, which is 3 millimeters. 3 millimeters is going to be 3 times 10 power negative 3 in meters. So this will be times 3 times 10 power negative 3 in meters. When you press your calculator, this is obvious. You get 6.0 times 10 power negative 5 Teslas. So that is the change in magnetic flux density for that thickness. That is the change in magnetic flux density for that thickness. Then the change in emitted frequency. So since they have given us that the frequency is equal to 2 CB, and we have got the change in magnetic flux density, so we shall just substitute 2 times C is given as 1.34 times 10 power 8, and the change in the magnetic flux density is 6.0 times 10 power negative 5. So 6 times 2 times 1.34 from my calculator. So my calculator is giving me 1.6 times 10 power 4. You can always check. I could be making a mistake. Okay, define the Tesla. Again, it is 3 marks. So you can define the Tesla as a unit of magnetic flux density. Or we just say flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere normal to the magnetic field experiences a force of 1 Newton per meter of its length. Flux density is 1 Tesla. Let me write that, although I wrote a different one earlier on, but it's the same thing. So we are saying flux density is 1 Tesla. Flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere normal to the magnetic field experiences a force of 1 Newton per meter of its length. Remember, 1 Tesla is equal to 1 Newton per ampere per meter. So you can think of the definition from this. Flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere normal to the magnetic field experiences a force of 1 Newton per meter of its length. That is the Tesla. Okay. A horseshoe magnet is placed on a balance. A stiff metal wire is clamped horizontally between the poles as illustrated here. The magnetic flux density in the space between the poles of the magnet is uniform and is 0 outside this region. The length of the wire normal to the magnetic field is 6.4 centimeters. That part of the wire which is normal to the magnetic field is 6.4 centimeters. When a current in the wire is switched on, the reading on the balance increases by 2.4 grams. That means the force on the magnet increases because the reading on the balance increases by 2.4 grams. So the force on the magnet increases. That means by Newton's third law, the force on the wire must be upwards. So state and explain the direction of the force on the wire due to the current. So since we have seen that the force on the balance is the force on the balance increases, because the mass is increasing, it means the force on the magnet is downwards. So originally there is a downward force on the magnet due to the current. So originally there is a downward force. There's a downward force on the magnet due to the current. And by Newton's third law, the force on the wire must be upwards. So if the reading of the balance increases by that, then it means by Newton's third law, if the reading on the balance is increasing, it means the force on the magnet is increasing downwards. So there is a downward force on the magnet due to the current, and by Newton's third law, the force on the wire must be opposed to that the force on the magnet. Okay. Calculate the magnitude of the flux density, that is B, between the poles of the magnet. So we know that the force is given by B. If the wire is normal to the field, the force is given by B. And this force is going to be equal to actually the weight. This force is going to be equal to the weight. And we know that the weight is given by M times G. So that force which is causing a change in the mass is going to be given by mg. So I will start from, I want to find B. So I will say B times the current. The current is 5.6 times the length of the wire, which is 6.4 centimeters. So that is 6.4 times 10 power negative 2. This should be equal to the weight. The mass is 2.4 grams. So I will say 2.4 times 10 power negative 3. Then times G, which is 9.81. So I press my calculator to find B. So from my calculator, this is divide. So from my calculator, I'm getting 0.066 Teslas. 0.066 Teslas. A low frequency alternating current is now passed through the wire in B. The root mean square value of the current is 5.6 amperes. Describe qualitatively the variation of the reading seen on the balance. Describe qualitatively the variation of the reading seen on the balance. So they are saying the root mean square value of the current is 5.6. That is the maximum. So how does the value vary? Because they have now replaced the directive current with alternating. The low frequency S is now passed through the wire. So first of all, we need to calculate the peak value. We know that I naught is equal to the square root of 2 times I root mean square. So this is going to be root of 2 times the I root mean square. And maybe just to calculate this, the root mean square is 5.6. So the peak value of current is actually, this is going to be root 2 times 5.6 amperes. Note that direct current, which was 5.2 amperes, was correspond to a change of 2.4 grams. That means the root means the peak value of current is going to correspond to a value of root 2 times 5, where there is 5.6 amperes. In terms of grams, in terms of mass, we shall replace the current with the mass. Therefore, we shall say that the mass corresponds to the peak value. So the peak mass, or the maximum value of mass, is going to be root 2 times 2.5. So this is going to be m naught is going to be root 2 times 2.5, 2.4 in grams. So this is going to be 3.4 grams. This is going to be the maximum mass. If that is very hard, you can think about this. If we had 5.6 amperes DC, this caused a change of 2.4 in grams. Now we have a maximum current of root 2 times 5.6 amperes. What change in mass will it cause? When you cross multiply these two, you have that x is equal to actually 2.4 times root of 2 times 5.6 divided by 5.6. So you notice that the mass corresponding to that peak is going to be 2.4 root of 2. So in our explanation, we shall say the new reading the new maximum reading so the new reading is 2.4 grams times root of 2, which is going to be equal to 3.4 grams. That is the maximum. So it means the mass now changes. The mass now changes between a positive 3.4 grams to negative 3.4 grams. And that means the total change, because they want the describe quantitative, that means we must quote values. So the total change in the mass, total change is going to be from positive 3.6 to negative 3.6. The total change is twice that, which is 6.8 grams. That is the total change. So the new reading, I've showed you how we come up with that new reading from this simple algebra. Or you can think of this directly if you're a very able learner, but this one is easy. 5.6 DC caused a change of 2.4 grams. Now we have alternating. What is the maximum change in mass that it can cause? For alternating, I naught is root 2 times I root mean square. So root 2 times 5.6 should cause a change x, which x can be got from cross multiplying these two equations. Okay. Next, we are going to describe the main principles of the determination of the charge on an oil drop by Millikan's experiment. You may draw a diagram. The best is to draw a diagram. I think the easiest is to draw a diagram. The explanation becomes easy. So I'm going to try and sketch a diagram. Although I don't have a rule, I will try my level best. So this is I think in electric fields. So we shall have horizontal metal plates. Let's have two parallel horizontal plates which have been connected to a voltage supply or a potential difference. So I will have a variable power supply here I'll just put there an arrow to show that is a variable power supply. I'll connect a voltmeter across. So I have a voltmeter across. You can draw a neat diagram. What is missing is the ammeter. I have to include the ammeter somewhere. So I'll put here the ammeter because I will need current. Okay, so the bottom plate is obviously negative. The top plate is obviously going to be positive. So an oil drop, I may introduce maybe a microscope here to be able to view the oil drop very well. So this is Millikan's experiment. So this is the microscope. If you want, you can name it. So an oil drops are going to be squeezed through the hole here, and we shall concentrate on one oil drop, which has been enlarged by the magnet. So we want this to experience two forces. One will be force due to gravity downwards, and will experience a force due to the electric field upwards. So this is the oil drop. The space is not enough, but I want to label this oil drop. This here we have a microscope. The other symbols, I think they hold their meaning. Let the distance between the two plates be d. Let the distance between the two plates, this distance here is d. That distance is d. Yeah, so my experiment is now ready. So how did Millikan perform this experiment? An oil drop is charged by friction as it is pushed out through a hole, a narrow opening from, say, a spray, and it is introduced between parallel horizontal metal plates. The PD between the two plates is adjusted until the oil drop is stationary. So we are saying, I think I'll start by writing the space here. So the microscope is showing that the oil drop is viewed through a microscope, and the mass m of the oil drop can be determined from the terminal speed of the drop when the PD is 0. So the oil drop is viewed through a microscope, and its mass m is determined from the terminal velocity or the terminal speed of the drop when PD is 0. Of course, when terminal speed is reached, when the PD is 0, of course, that is just falling due to air resistance balancing the weight. So you can find its mass when the terminal speed of the from the terminal speed of the drop when the PD is 0. We can be able to determine its mass. So we have determined m. So what happens is to now charge the oil drop. So we are saying the oil drop is charged. The oil drop is charged by friction as it is pushed. The oil drop is charged by friction as it is pushed through a hole. through a hole and it is introduced. It is introduced between parallel horizontal plates. Between parallel horizontal metal plates. Okay, so now what happens is that the PD is going to be adjusted. The PD is adjusted. The PD is adjusted until the oil drop is stationary. Until the oil drop is stationary. And when it is stationary, of course, it means that mg, which is its weight, is going to be Q times V over D, where m is its mass, G is acceleration of free fall, Q is the charge, of the oil drop, and then V is the PD, V is potential difference, and then D is the separation of the plates. So notice that the marks are too many, that's why I had to write a lot, that is 7 marks. So drawing the diagram reduces the writing. Of course, instead of I've indicated a microscope here, I may not write oil drop is viewed through a microscope. Its mass is determined from the terminal speed of the drop when the PD is 0. Then the oil drop is charged by friction as it is pushed through a hole and it is introduced between parallel horizontal metal plates. The PD is adjusted until the oil drop is stationary. That is mg is equal to qvd, v over d. And I define all the letters that I've used here. So this gives me, I think, 7 marks. Defining the letters, 1 mark. Adjusting the PD, and that is already 3 marks. How the oil drop is charged, those are 4 marks. And it is introduced between 2 parallel horizontal plates, as I can see from the diagram, those are already 5 marks. The PD is going to be adjusted. I can see the microscope there, those are already 6 marks. So it's like all the 7 marks are covered in that case. In an experiment, to determine the fundamental charge, values of charge on oil drops were found by a student to be as shown. State the value to 2 significant figures of the fundamental charge that is suggested by these values of the charge on the oil drops. Of course, when you look at these charges, you notice, first of all, you'll be checking them to see which one is a multiple of 1.6 times 10 power negative 19 coulombs. This one is not a multiple. Although this is almost a multiple, this is almost a multiple, this is a multiple, this is, I think it is a multiple. So you are going to notice that actually the smallest multiple of E is this one here. 3.6 is the smallest multiple of E. So they said state the value to 2 significant figures of the fundamental charge that is suggested by these values of charge on oil drop. So I'm saying the answer is 3.2 times 10 power negative 19 coulombs. It is the smallest multiple of E. So that one is the smallest. It is the smallest multiple of 1.6 times 10 power negative 19 coulombs. Therefore, I will go with this one here. So the charge, the fundamental charge which is suggested by these values is 3.2 times 10 power negative 19 coulombs, because it is the smallest multiple of 1.6 times 10 power negative 19 coulombs. That is the explanation. Okay, next. The plane PQRS has area A. The plane PQRS has area A. State what is meant by a magnetic field. We have said the magnetic field is a region of space where a moving charge or a magnetic pole, a magnetic material experiences a force. So I will simply say a region of space, region of space, region of space where I can say a moving charge may experience a force. Or a force is produced by a moving charge. You can also talk about the magnetic pole. You can also replace this with a magnetic pole. You can replace this with a magnetic pole. You can replace it with a magnetic material. You can replace it with a current carrying conductor. So all those, you just choose one. That is going to be a magnetic field, a region of space where a magnetic pole may experience a force, or a force is experienced due to a magnetic pole, or a force is created by a magnetic pole. That is a magnetic field. A force is experienced due to a current carrying conductor. A force is produced by a current carrying conductor. That is a magnetic field. Okay. An expression in terms of A, B, theta for the magnetic flux phi through the plane PQRS. Of course, phi is given by BA sine theta. Reason: the angle given is between the plane of the area and the magnetic field, and we are interested in the normal to the plane. So resolving normal to the plane to be sine. So that is going to be BA sine theta. Then a vertical aluminium window DEFG has a width 52 centimeters and length 95 centimeters as shown here. The frame is hinged along the vertical edge DG. The horizontal component BH of the Earth's magnetic field is given as 1.8 times 10 power negative 5 teslas. For the closed window, the frame is normal. When it is closed, the frame is normal to the horizontal component BH. The window is opened. That means now it is going to be parallel. The plane of the window rotates through 90 degrees. Explain why, when the window is open, the change in magnetic flux linkage due to the vertical component of the Earth's magnetic field is zero. The change in magnetic flux linkage due to the vertical component of the Earth's magnetic field is zero. So we are saying when the window is opened, the plane of the frame is always parallel to B. The plane of the window is always going to be parallel to BV. So the flux linkage is going to be zero. So when the plane is parallel, when the window is opened, the plane of the frame is always parallel, because we are talking about the vertical component of the Earth's magnetic field. When the window is open, the plane of the frame is always going to be parallel to the vertical BV. Plane of the I'm going to use BV for the Earth's vertical component of the Earth's magnetic field. not the horizontal, that is BV, that is the earth, the vertical component of the earth's magnetic field. So the plane of the frame is always parallel to the earth, to the vertical component of the earth's magnetic field. So it means the flux linkage is always zero. So the flux linkage is always zero. So whether the window is opened or closed, the vertical component of the earth's magnetic field is always parallel to the plane of the frame. That means the flux linkage is always zero, and therefore it means the flux linkage is always zero due to the Earth's vertical component. Therefore, it means the change in the magnetic flux linkage or change in magnetic flux linkage will always be zero. Okay, part 2. Calculate for the window opening through an angle of 90 degrees the change in magnetic flux linkage. So when it is closed, the flux is going to be B times A. So the change in flux, because when it is open, it is just zero, flux linkage is zero. So the change in flux is going to be B times A, which is going to be 1.8 times 10 power negative 5, that is B. Then the area is going to be, we have 52 by 97, that is the area. So we shall have 52 times 10 power negative 2 by 95 times 10 power negative 2. I'm changing it to meters. Then I press my calculator. So when I press my calculator, I'm getting 8.9 times 10 power negative 6. That is the change in flux linkage. Okay, next, state Faraday's law of electromagnetic induction. We know that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. The window is opened in a time of 0.30 seconds. The window is opened in a time of 0.30 seconds. Use your answer in B Roman 2 to calculate the average EMF induced in the window. That is just 1 mark. So that is very easy. The EMF is simply going to be the change in flux divided by time. So the change in flux, we have calculated it as 8.9 times 10 power negative 6 divided by the time, which is 0.30. Of course, we are going to assume that the EMF gradually changes from maximum to 0 when the window is opened. So here we shall not multiply by 2. So it is a steady decrease from maximum to 0 when the window is opened. So the EMF is going to be 3.0, I think. This is approximately 9. That is 3.0 times 10 power negative 5 volts. That's just 1 mark. State the size of the window frame between which the EMF is induced. State the size of the window frame between which the EMF is induced. I think this is a wrong question, and I think this question must have been removed in that series, because when you say state the size of the window frame between which the EMF is induced, this question does not give any meaning. It does not give any meaning. State the size in which the EMF is induced. If the magnetic field is normal to the plane of the window, then this, I think it wanted to talk about it wanted to bring in the concept of magnetic fields and electric fields. So maybe wanted to talk about Hall voltage, but this question does not give any serious meaning. So this question was removed in that series, and every student must have been given 1 mark. That one I'm very sure. Okay, next. A particle has mass m and charge positive q and is traveling with speed v through a vacuum. The initial direction of travel is parallel to the plane of two charged horizontal metal plates as shown here. The uniform electric field between the plates has magnitude 2.8 times 10 power 4 volts per meter and is zero outside the plates. The particle passes between the plates and emerges beyond them as shown. Explain why the path of the particle in the electric field is not. In an electric field, the path is not an arc of a circle, it is actually a parabola. So why is the path not an arc of a circle? That one is very simple. We know that the force in the electric field is always along the field. In fact, the force is normal to the plates. It's not normal to the direction of motion of the particle. So the force is in the direction of the field, in the direction of the field. The force here is normal to the plates, not normal to the direction of motion of the particle. So the force is in the direction of the field, that is normal to the plates. Therefore, it does not provide centripetal force. The force is normal, is in the direction of the field, that is normal to the plates, so it does not provide centripetal force. So it does not provide centripetal force. The force due to the electric field is normal to the plates, or is just along the direction of the field. So it does not provide the centripetal force. So not circular at all. So note the difference between this and the electric field, where the force due to the magnetic field, where the force provided the centripetal force. Alternatively, the constant speed is parallel to the plates. That one should also guide you to that. The constant speed was parallel to the plates. It is always parallel to the plates because the force is in the vertical. So the constant speed is parallel to the plates. The constant speed is parallel to the plate. Therefore, there is no way this force will provide a centripetal force to cause circular motion. So we are saying the force in an electric field is in the direction of the field, or it is along the field. It is actually normal to the plates. So it does not provide centripetal force. So not circular. For a force to provide centripetal force, it must be always perpendicular to the direction of motion of the particle. Yet this one is not depending on the direction of the motion of the particle. It is just perpendicular to the plates, so it is along the field. Okay. A uniform magnetic field is now formed in the same region between the plates. The magnetic field strength is adjusted so that the positively charged particle passes undeviated. Okay. State and explain the direction of the magnetic field. State and explain the direction of the magnetic field. Okay. So since the electric field is downwards, the particle is positively charged, So it means the force due to the electric field is downwards. For a positively charged particle, the force is in the direction of the field. For it to pass through undeviated, this is the force due to the electric field. The force due to the magnetic field must be upwards. B must be upwards. Now we want the direction of the field. So hold your first finger to point in the same direction as, but can't I search this? I think I have internet. I want to bring Fleming's left hand rule here or right hand rule here. Let me try. Okay, I'm trying to bring Fleming's left or right hand rule. Whatever we shall get will help us to get this. Maybe people will see this and will appreciate it. I'm trying to contact the sketch lab. Okay, I hope it is loading. Okay, so as it loads, I am saying, try to hold your first finger. Try to hold your first finger in the direction of, actually the second finger in the direction of the particle because the particle is positive. Try to hold the second finger in this direction to point to the right, and the thumb should be pointing upwards. That is up the plane of the page. The thumb is pointing upwards, that is up the plane of the page. You notice that when you hold the the second finger in this direction, with the thumb pointing up the plane of the page, then you are going to notice that actually the first finger is pointing to the page. I don't know why it is not loading. Okay, when it is ready, I'll come back to it. For now, let me give it a break. So, meanwhile, as it is loading, we are trying to estimate the direction, or to get the direction of, we are trying to find the direction of the magnetic field. And I said, Place your second finger in the direction because the particle is positive. If it was negative, we would reverse the second finger to point in the opposite direction. But since it is positive, the second finger points in the same direction as the particle. Then since the particle is to pass undeviated, it means because the force due to the electric field is downwards, the force due to the magnetic field should be upwards. And when you hold your paper on table, if it is on table, you notice that the first finger must point to the table, for the second finger to point towards the right, and the thumb to point upwards. That is, if your paper is on the table. Therefore, the direction of the force due to the magnetic field must be opposite to that due to the electric field, because they wanted us to explain. So I will say the direction of the force due to the magnetic field the direction of the force due to the magnetic field must be or is opposite, is going to be opposite. Since this is not loading, I will first close it. I will open it later on. Maybe my internet has problems. So the direction of the force due to the magnetic field is opposite to that due to electric field. It is opposite to that due to the electric field. So it means the force due to electric field is down, and we know that the force due to electric field is downwards. Therefore, the force due to the magnetic field must be upwards. So we shall say since the force due to the electric field is downwards, the force due to the magnetic field is upwards. So that means by Fleming's left-hand rule, the field is into the page. By Fleming's, I'll just write FLHR, Fleming's left-hand rule, the field is into the page. The field is into the plane of the page. By Fleming's left-hand rule, the field is into the plane of the page. I don't know whether if it has downloaded, but I think it is not downloading. Okay, so we shall see if we get it next time. Part 2, the particle has speed 4.7 times 10 power 5. Remember, it passes through undeviated, and if it passes through undeviated, it is because the force due to the magnetic field is equal to the force due to the electric field. So we say BQV is equal to Q times E. That means B is going to be equal to, because Q has cancelled, B is going to be equal to E over V. So we now substitute. B is going to be equal to E. The electric field has been given as what is the electric field? 2.8 times 10 power 4. So 2.8 times 10 power 4 volts per meter. The speed is 4.7 times 10 power 5. Then we press our calculator. This is very simple. Divide. So this is 6.0 times 10 power negative 2 Teslas. 6.0 times 10 power negative 2 Teslas. The particle in B has mass m and the charge q and speed v. Without any further calculation, state the effect, if any, on the path of the particle that has mass m, charge negative q, speed v. Without any further calculation, state the effect, if any, on the path. We want the path of a particle that has the mass is the same, the charge has just changed sign, the speed is v. So if the speed is not changing, then there is no change because v is independent of the charge and the mass. So there is no change. No change, or you could say no deviation still, or not deviated. Simply because v, as long as v is constant, then the path is not affected. The direction of the deflection is depending on the speed. The mass is m, the charge is q, the speed is doubled. So because the speed is doubled, it means that bqv must be greater than q times e. The speed is doubled. That means the force due to the magnetic field is greater than the force due to the electric field. Therefore, it is deviated upwards. So this is deviated upwards. Deviated upwards. Then the mass is 2m, the charge is q. As long as the speed is the same, there is no change. So this is no change because the deflection does not depend on the mass or the charge. So there is no change. No change, or we can say not deviated again. Not deviated. The deflection is not depending on the charge or the mass. Next, an incomplete diagram of the magnetic flux pattern due to a current carrying solenoid is illustrated here. On the figure, draw arrows on the field lines to show the direction of the magnetic field. When you follow through the current, you notice that the current goes behind and comes back as pointing upwards like this. So the current in this coil is like that. It goes backwards and then it comes out like that. So on the figure, we want to draw arrows on the field lines to show the direction of the magnetic field. So use the right hand grip rule. Grip your pen in your hand to act as the coil, with the fingers pointing the same direction as current. When the four fingers point in the same direction as current, when you grip your pen, you notice that the thumb points to the left. So it means the left is going to be the magnetic north and the right is the magnetic south for this particular coil of wire. Therefore, the field lines, remember, originate from north and terminate to the south. Therefore, the arrows will be in that direction. As simple as that. State the feature of the figure that indicates that the magnetic field at each end of the solenoid is less than that at the center. Of course, you see at the end, the field lines move apart. Yet, that means the field weakens, and you also see the spacing at the end is greater than that at the center. So the lines are more spaced out at the ends. That makes the field there to be different or to be less. So the lines are more spaced. The lines are more spaced out at the ends. That makes the field there to be less stronger, or the field strength to be less than at the center. A hollow probe is placed near one end of the solenoid in A, as shown here. So the whole probe is placed at one end of the solenoid, and this is what is shown here. The probe is rotated about the axis XY. State and explain why the magnitude of the Hall voltage varies. Why does the magnitude of the Hall voltage varies when it is rotated? We know that VH is equal to BI over NTQ. If N, T, Q, and I are constant, then VH is depending on B, and B depends on the angle. So this depends on the angle, so it can be B sine theta. When the whole probe is rotated, of course, the angle varies. The angle changes from 0 when the plane is parallel to the field to maximum or to 90 degrees when the plane is perpendicular to the field. So the whole voltage depends on the angle. The whole voltage depends on the angle. That is 1. So we are saying the whole voltage depends on the angle between the field and the plane of the probe. The whole voltage depends on the angle between the field and the plane of the probe, and it is going to be maximum when it is 90 degrees and is maximum when the field is normal to the plane. The field is normal to the plane of the probe and is 0 when the field is parallel to the plane of the probe. When the field is parallel to the plane of the probe. Okay. State Faraday's law of electromagnetic induction. That one is now a familiar question. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. The hollow probe in B is replaced by a small coil of wire connected to a sensitive voltmeter. State 3 different ways in which an EMF may be induced in the coil. State 3 different ways. We have seen the hollow probe has been rotated. The hollow probe was rotated. Now we want 3 different ways in which an EMF may be induced in the coil. Number 1, of course, we can rotate the coil. We can rotate the coil itself. We can rotate the coil. Number 2, you can move the coil towards or away from the solenoid. So we can say move the coil. Because they have removed, the hollow probe has been replaced by a small coil, and we want an EMF to be induced. Yet in the coil, which we have there, we have a direct current. So if you want an EMF to be induced in a coil caused by direct current, then you have to move the coil towards or away from the solenoid. That is number 2. Number 3, you can vary the current in the solenoid. Vary the current in the solenoid. To vary the current means increase the current or decrease the current. Number 4, you can insert a soft iron core in the solenoid. Insert an iron core. Insert an iron core into the solenoid. That one still changes the magnetic flux into the solenoid. You can insert an iron core into the solenoid. That still changes the magnetic field That means an EMF will be induced in the neighboring coil. You can also switch on or off. You can also switch on or off current in the solenoid. Switch on or off current in the solenoid. Switch off or on current in the solenoid. You could also use SC, connect the solenoid to SC. Here I said switch on or off. You can also connect the solenoid to alternating current. So all these ones are some of the ways you are going to induce an EMF in the coil which is kept or which is placed near a solenoid. Okay, you can't fail to state at least three. Number next, a charged particle of mass m and charge negative q is traveling through a vacuum at constant speed v. So these are the parameters. It enters a uniform magnetic field of flux density b. The initial angle between the direction of motion of the particle and direction of the magnetic field is 90 degrees. Explain why the path of the particle in the magnetic field is an arc of a circle. The path is an arc of a circle. We say the magnetic force is constant and always normal to the direction of motion. So magnetic force is constant and always normal to the direction of travel of motion of the particle. It is always normal to the direction of motion of the particle. What does that mean? The speed does not change. So speed remains constant. That means kinetic energy is constant. If the speed remains constant, no work are done. All those ones. Speed is constant, no work are done. Kinetic energy is constant. All those ones. So this force just provides the magnetic force. I mean the centripetal force. So the magnetic force just provides centripetal force. The magnetic force just provides centripetal force. As simple as that. Okay. The radius of the arc is r. Show that q over m is for the particle is given by that. That is charge to mass ratio. Since the magnetic force provides the centripetal force, since it's just one mark, I will just equate. That is B QV is equal to mv squared over r. Rearranging v has cancelled. Rearranging q over m is going to be mv. M has gone the other side, so we will just have v divided by b times r. As simple as that. The initial speed v of the particle is 2.0 times 10 power 7. The magnetic flux density B is 2.5 times 10 power negative 3. Calculate the charge to mass ratio. The radius of the arc is given as 4.5. So the charge over mass is going to be equal to 2.0 times 10 power 7 divided by B is 2.5 times 10 power negative 3 and R is the radius is 4.5, so it will be 4.5 times 10 power negative 2. When I put my calculator here, So from my calculator, this is 1.8 times 10 power 11 coulombs per kilogram as the ratio. The path of the negatively charged particle before it enters the magnetic field is shown here, as you can see in the diagram. The direction of the magnetic field is into the plane of the paper. So the field is into the plane of the paper, so the second finger should be pointing to the paper. Why can't I find this? I really need this model. Let me try again. Okay, let's try again and see if it loads this time, because internet might be the problem. Okay, it is loading this time. We thank God. Yes. So we have here the Fleming's left-hand rule. Although it is hard to use in 3 dimensions, I will try to use it, no problem. So here we have this is you have your paper on table there, and we are going to use Fleming's left-hand rule because the question is telling us, the first question is telling us, actually it is telling us that the direction of the magnetic field is into the plane of the paper. That means the first finger is going, hold your first finger like that, the way you see in this animation. This is the thumb. Somewhere here we have the thumb. This is the thumb. And we have here the first finger and the second finger. So you are going to hold your first finger to point into the paper. So I'm rotating this point onto the paper, assuming that is the paper. So first finger should point onto the paper. And unfortunately, the particle given is negatively charged. So instead of the second finger pointing the direction, as you see this animation here, instead of the second finger pointing that direction, you are going to reverse it. Only that this one cannot be reversed. That is the challenge. But look at the second finger. Instead of pointing like that, you are going to reverse the second finger to point in the opposite direction. That is, in this animation, the second finger is pointing to the right. So you rotate your hand through 180 degrees. That is going to be actually clockwise. I mean anti-clockwise. This animation is not complete. It cannot easily rotate. So its rotations are limited. Its rotations are limited, but I can try to rotate it. Its rotations are limited. It is hard to make it rotate in the correct way I wanted it. But making the second finger point in the same direction as you can see in that direction, that is opposite to the direction of the particle because the particle is negatively charged. When you have a negatively charged particle, the second finger points in the opposite direction. So with the first finger pointing to the page, as we had already seen, it is hard to make the first finger point to the page. For this kind of animation, it doesn't rotate in all directions. That is the problem. So make the first finger point onto the page like that, and then reverse the direction of the second finger to point in the opposite direction. Then you are going to see, when you rotate this, you rotate the second finger through 180 degrees to point that direction, the thumb is going to be pointing downwards. The thumb is going to be pointing downwards. When you rotate the second finger to point to the left, the thumb is going to point downwards. For that reason, it means the force on the particle when it enters the magnetic field is going to be downwards. And if the force is downwards, then it means the magnetic force is going to produce a centripetal force, which causes the particle to move at an arc downwards. Therefore, I'll draw a path here, which is going to be a tangent to this straight line. It is just a tangent, but then the path goes on, it becomes a circular arc. Then when it emerges, of course, when it emerges, you put there a ruler and draw a straight line, which is a tangent. At the point of emerging, you put there a ruler and draw a straight line, which is a tangent. So let me first close this hand. At the point of emerging here, it should be a straight line. That is outside the field. It should be a straight line. So this should be a very nice tangent to the curve. To the straight line. It is just a perfect tangent. No kinks. Then should be a tangent, and when it emerges, you put there a ruler and draw a straight line which is a tangent to your curve, A straight line which is a tangent to the curve. Don't draw a line which is not a tangent to the curve. It should be a perfect tangent to the curve. Okay, so the path is going to be downwards. If you wanted to draw a better curve, you can even draw one which is more better than mine. But then as it emerges, you just put a what? A straight line with a ruler. It should be a straight line here. This part here should be extremely straight using a ruler, but not disobeying, but should still be a tangent to the curve. So I can rub off this maybe. So when it emerges, please draw a straight line with a ruler, which is a tangent to the curve. The line should not be bending into the curve. It should just be a perfect tangent to the curve. Okay, as simple as that. So please have tried my level best to use Fleming's left-hand rule, even though the animation was not rotating through 360 degrees. Okay, next, define the Tesla. Define the Tesla. I think we have now defined the Tesla. I will still define it in another simpler way. So you can always choose the one which you think is the easiest for you to comprehend. So the magnetic flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere experiences a force of 1 Newton per meter of its length. That is a Tesla. The magnetic flux density is 1 Tesla. So I'll simply say flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere normal to the magnetic field experiences a force of 1 Newton per meter of its length. Of 1 Newton per meter of its length. Flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere I can even add normal to a uniform magnetic field experiences a force of 1 Newton per meter of its length. That is a Tesla. A long solenoid has an area of cross-section which is 28 centimeters squared, as shown here. Okay. A coil C consisting of 160 turns of insulated wire is wound tightly around the center of the solenoid. The magnetic flux density B at the center of the solenoid is given by the expression B is equal to mu naught N times I. Of course, we know from the list of constants, mu naught is going to be 4 pi times 10 power negative 7. That is given the list of constants, that is mu naught, which is called the permittivity of free space, permeability of free space, not permittivity. Okay, N is a constant which is equal to 1.5 times 10 power 3 per meter. Calculate for a current of 3.5 amperes in the solenoid, the magnetic flux density at the center of the solenoid. So we know flux density is going to be given by that expression mu, which mu is 4 pi times 10 power negative 7, that is permeability of free space, which is always given, then times N is 1.5 times 10 power 3, then the current is 3.5. There's nothing here, the two marks are free, just substituting. Pressing the calculator, this is 6.6 times 10 power negative 3. Of course, aim at always writing at least two significant figures if the answer is not exact in physics. Then the flux linkage in the coil, C, flux linkage, magnetic flux linkage. We know that flux linkage is equal to NBA, as my students prefer to state it. So flux linkage is equal to NBA. So just substitute N, number of turns was 160, times the magnetic flux density. We have calculated it as 6.6 times 10 power negative 3, I guess, times 10 power negative 3. Then times the cross-sectional area. They gave us the area was 28 centimeters squared. The area is 28 centimeters squared, so this is going to be 28 times 10 power negative 4 to change it to meters squared. So that is going to be 28 times 4, 28 times 10 power negative 4 to change it to meters squared. So I press my calculator. So this is giving me 3.0 times 10 power negative 3 to three significant figures. I hope I calculated it correctly. 160, 6.6, 28. Yes, it is 3.0 times 10 power negative 3 Weber. State Faraday's law. Don't get tired of stating Faraday's law. It should become part of you. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The current in solenoid B is reversed. That is a very important point there, reversed in that time. The current is reversed. Can show the average EMF induced in the coil C. So the EMF here is simply going to be the change in flux with the time, but we are going to multiply this by 2 or divide the time by 2. So this is going to be 3.0 because the current was reversed. 3.0 times 10 power negative 3 over time. That is over time is 0.80, but we shall divide the time by 2, which is the same as multiplying the answer just by 2 if instead of dividing the time by 2. So this is the same as 2 times 3.0 times 10 power negative 3 divided by 0.80. Because the current was reversed, that's why the 2 is coming in. If it wasn't reversed, that 2 would not come in. So the shear flux linkage over time, that is EMF, just divide times 2, divide by that. And this is giving me 7.4 times 10 power negative 3 volts. Find the Tesla. Find the Tesla. We have said the magnetic flux density is 1 Tesla. Flux density is 1 Tesla when a long straight conductor or wire, when a long straight conductor carrying a current of 1 ampere normal to a uniform magnetic field experiences a force of 1 Newton per meter. 1 Newton per meter of its length. That is a Tesla. A long straight conductor carrying a current of 1 ampere normal, this is very important, that is perpendicular to a uniform magnetic field, experiences a force of 1 Newton per meter of its length, that is a Tesla. 2 long straight vertical wires X and Y are separated by a distance of 4.5 centimeters. The wires pass through a horizontal plane, a horizontal card as shown here. The current in X is 6.3 in the upward direction. Initially, there is no current in Y. On the figure sketch in the plane PQRS, the magnetic flux pattern due to the current in wire X show at least 4 flux lines. So grip your pen in your right hand with the thumb pointing upwards because the current is coming upwards. It is coming out of the page. So 1, the field lines are going to be concentric circles because the fingers fold anti-clockwise, as you can see. So we shall draw concentric circles around the wire. They should be concentric circles. Use a compass to draw neat circles whose separation starts to increase as you move away from the wire. The separation starts to increase as you move away from the wire, indicating that the field strength reduces as you move away from the wire. Use a compass to draw a neat diagram. So the field lines are in the same direction in which the fingers fold when you hold your pen, when you grip your pen with the right hand. With the thumb pointing upwards, the fingers fold in the anti-clockwise direction. Okay? The magnetic flux density B at a distance x from a long current carrying wire is given by this expression here, where I is the current in the wire, mu is the permeability of free space. Remember, permeability is 4 pi times 10 power negative 7. calculate the magnetic flux density at wire Y due to the current in wire X. Calculate the magnetic flux density. So we are substituting the magnetic flux density B. These two marks are just for free, just substituting. B is going to be 4 pi times 10 power negative 7, that is mu. They told us the current was 6.3. So the current is 6.3 divided by 2 pi times x. That is, calculate the magnetic flux density at wire Y due to the current in wire X. So the distance is the separation of the two wires, which is 4.7 centimeter, 4.5 centimeters. So this will be 4.5 times 10 power negative 2. Just press your calculator. So from my calculator, I have 2.8 times 10 power negative 5. 2.8 times 10 power negative 5. Okay, next, a current of 9.3 is now switched on in wire Y. Use your answer in part 2 to calculate the force per unit length on wire Y. Of course, the force on wire Y due to its current is going to be given by Bill. Of course, it is Bill sine theta, but since it is the field at the position of the wire is normal to the current, then sine theta is going to be 1. So this is going to be Bill sine theta. The force per unit length is what I want to find. So the length is 1 meter. Of F over L is going to be B times the current I, which is B is now the magnetic. It is the magnetic flux density. It is in the magnetic, calculate the magnetic flux density at wire Y due to wire X. It is in the magnetic field of wire X, which is 2.8 times 10 power negative 5. And the current in it is 9.3. So just press our calculator. Of course, sine theta is 1, so that one is not a problem because it is the current is normal to the field of the wire. It is just at a tangent. The tangent along the plane of the wire, that is for the field caused by this. And yet the current is vertically upwards. So that one means the force is going to be, force per unit length is 2.6 times 10 power negative 4. 2.6 times 10 power negative 4. Okay. The currents in the two wires in B Roman 3 are not equal. Explain whether the force per unit length on the two wires will be the same. Of course, the force is the same because the force per unit length, it depends on the product of the wires. So it is the same for both. It does not depend on the magnitude of the currents. It depends on the product. It is proportional to the product of the currents. So we are saying the force per unit length is proportional to the product of both currents. Is proportional to the product of both currents, so it is the same. So it is the same for both. Do not forget Newton's third law. So somebody would also say by Newton's third law. I'll just write N3 to mean Newton's third law. By Newton's third law, the forces are equal but in opposite direction. But in opposite directions. Okay, What do we mean by quantization of charge? Quantization of charge. From Millikan's experiment, charge was taking on specific values which were integral multiples of the elementary charge. So when we talk about quantization of charge, we mean charge exists in discrete and equal quantities. Charge exists in discrete and equal quantities. Charge exists in discrete and equal quantities, or we simply say charge exists in multiples of 1.6 times 10 power negative 19 coulombs. That is the elementary charge. So we can say charge exists in multiples of 1.6 times 10 power negative 19 coulombs. That is what we mean by quantization of charge. Charge is discrete, takes on specific values which are multiples of 1.6 times 10 power negative 19 coulombs. Okay, part B. The charged parallel plate, as shown in the figure, produce a uniform electric field between the plates. So we have protons, so it means the force on the protons is downwards due to the electric field. The electric field outside the region between the plates is zero. A uniform magnetic field is applied in the region between the plates so that the beam of protons passes undeviated. So the magnetic force must be upwards. Magnetic force must be upwards. State the direction of the magnetic field between the plates. So the particles are protons, they are entering that direction. I think I should again bring back my model. It could be of help here. Let me try to bring back the model. I hope it will be of help. Bring back my model here. Okay, state and explain the direction of the magnetic field. So this time the model loaded very fast, that is fine. So we want to use Fleming's left-hand rule. So this is Fleming's left-hand rule. We want the first finger, of course, the second finger points in the same direction as the field. As the particle. So because the particle is a proton, the first finger will point to that side. So I'll make my first finger point to the right as that. And the thumb is automatically pointing up of the page, as you can see. So you see that the first finger is pointing to the page. Using this model here, you must be seeing if I make the second finger point in the same direction as the particles, and I try to make the thumb point upwards because the force due to the magnetic field is upwards, then the first finger is going to be pointing to the page, as you can see. Therefore, it means the field is going to be into the page, because the force due to the magnetic field must act upwards to balance the force due to the electric field, which is downwards. And if that is true, then using Fleming's left-hand rule, the field must be into the plane of the paper. So we can say that the force due to the magnetic field, must be upwards. The force due to the magnetic field must be upwards. Since the force due to the electric field is downwards, And by Fleming's left-hand rule, by Fleming's left-hand rule, the magnetic field, I will call it the B field, the magnetic field must be into the plane of the paper. The magnetic field must be into the plane of the paper. As simple as that. The magnetic field must be into the plane of the paper. Then part 2, they are saying the magnetic flux density between the plane is now increased. On the figure, sketch the path of the protons between the plates. They have increased the magnetic flux density. That means the force due to the magnetic field upwards is greater than the force due to the electric field. So what does that mean? The particle will just move upwards. So the particle will take that path. It should note that it should be a perfect tangent. And when it emerges, you put a ruler and draw a very perfect straight line. This part here should be very straight. So here I use a ruler to draw a very perfect straight line. And it should also be a tangent to the curve. As simple as that. A tangent to the curve. Okay, so I can now close my hand here. Next, a light spring is suspended from a fixed point. A bar magnet is attached to the end of the spring as shown here. So you can look at this. Okay, in order to shield the magnet from draughts, a cardboard cap is placed around the magnet but does not touch it. The magnet is displaced vertically and then released. The variation with the time t of the vertical displacement y of the magnet is shown here. So you can look at the variation. So you must have looked at the graph very carefully. The mass of the magnet is 120 grams. The mass of the magnet is 120 grams. For the oscillations of the magnet, use the figure 1.2, that is the graph, to determine the angular frequency omega. Of course, we know from other units that omega is 2 pi divided by t. So all we need is the period from our graph. And for one complete cycle, I think you notice that the period is going to be either 0.2 from there, or you look at this point here and this point here. That is going to give us the period, which is, I think, 0.3. The period is 0.3. So when I divide, so this is going to be 2 pi divided by 0.30. I press my calculator. So from my calculator, I'm getting 20.9 as the angular velocity. or angular frequency in that for that matter. Then show that the maximum kinetic energy of the oscillating magnet is 6.4 millijoules. Show that the maximum kinetic energy of the oscillating magnet is 6.4 millijoules. So we know from simple harmonic motion that energy, of course, energy here, since it is kinetic, you can think of it as half mv squared. But remember, v, maximum velocity v was equal to omega times x naught. That means the energy is going to be a half m omega squared. When you substitute v naught into this expression, the kinetic energy is going to be a half m omega squared times x naught squared. So we now just substitute. This will be a half times the mass is given as 130. 130 grams is 0.130 times omega. We have calculated it as 20.9, but is squared. Then times maximum displacement from the graph. I think this is 1.5. So the maximum displacement is 1.5 centimeters. So 1.5 times 10 power negative 2 squared. Then I press my calculator to verify. Half times 0.113 times 20.9 squared times 1.5 exponent negative 2 squared. So this is giving me to two significant figures, 6.4 times 10 power negative 3 joules, which is of course the same as 6.4 millijoules. You can verify also. The cardboard cup is now replaced with a cup made of aluminium and of aluminium foil. During 10 complete oscillations of the magnet, the amplitude of vibration is seen to decrease. Amplitude is seen to decrease to that value. The change in angular frequency is negligible, so the angular frequency is not changing for that matter. Use Faraday's law of electromagnetic induction to explain why the amplitude of the oscillations decreases. So let's go back to the experiment. This is a cardboard cup. Okay, we have a magnet. Of course, we don't expect an EMF to be induced in the cardboard cup. I don't think so. But the cardboard cup is replaced with aluminium, which is a what? A conductor. So now we have a conductor and we have a magnet which is moving. So that means the conductor should be cutting the magnetic field of the magnet. So we are saying as the magnet moves, the flux is cut by the aluminium cup. We have introduced an aluminium cup. So as the magnet moves, the flux is cut. Flux is cut by the aluminium cup. Of course, by Faraday's law, an EMF is induced. By Faraday's law, an EMF is induced, which gives rise to a current. So an EMF is induced by Faraday's law. By Faraday's law, an EMF is induced, which gives rise to currents and heating of the cup, which gives rise to eddy currents. Eddy currents that cause heating of the cup. Eddy currents that cause heating of the cup. So As the magnet moves, the flux is cut by the aluminium cap, and by Faraday's law, EMF is induced, which gives rise to eddy currents that cause heating of the cap. The thermal energy which is heating the cap is derived from the oscillations of the magnet, so the amplitude decreases. So the thermal energy which is heating the cap, thermal energy is derived. The thermal energy which is heating the cap is derived from the oscillations, of the magnet. So the amplitude reduces. I'm writing like this because I may need another space to give some alternative. So the amplitude decreases. That is one way of looking at this. As the magnet moves, the flux is cut by the aluminium cap. An EMF is induced in the cap by Faraday's law. This induced EMF gives rise to eddy currents in the cap, which cause heating of the cap. The thermal energy which is heating the cap is being derived from the oscillations of the magnet. So it means the oscillations are dying out, the amplitude decreases. Alternatively, instead of talking about eddy currents causing heat, the eddy currents may instead create another magnetic field which opposes the change producing it. So we can say, oh, the induced EMF gives rise to eddy currents which generate another EMF, or which generate another magnetic field that opposes the motion of the magnet. So we can say the induced EMF gives rise to eddy current currents which generate a magnetic field, Now the eddy currents themselves are generating a magnetic field in the aluminium cap. This field, that magnetic field which has been created, this field opposes or causes an effect that opposes the motion. It will cause a force which opposes the motion of the magnet. This field opposes the motion of the magnet, so the amplitude decreases. The field which is created is going to act so as to oppose the change producing it. That is in accordance by Lenz's law. Okay. Show that the loss in energy of the oscillating magnet is 4.8 millijoules. The loss in energy of the oscillating magnet is 4.8 millijoules. So the amplitude decreases to 0.75. Let's check the energy at 0.75. You will notice that also at 0.75, that is actually a quarter of the amplitude, yet we are seeing the energy is directly proportional to the amplitude squared. That means if the amplitude is halved, 0.75 is a half of the amplitude, it means the energy is going to be a quarter. So it means energy is going to be a quarter of the original amount of energy. That means it will be a quarter of 6.4, which is 1.6 millijoules. So that means the loss is going to be 6.4 minus 1.6, which is 4.8 millijoules. That is the easiest way for mathematicians, but for non-mathematicians, you can find at 0.75 centimeters as x naught, the energy is going to be a half times the mass, which was 0.130, times omega was 20.9 squared because its change was negligible, times the amplitude, which is 0.75 times 10 power negative 2, and this is squared. When you press your calculator, Let me check. So from my calculator here, I'm getting this energy as 1.6 millijoules. And if I try to find the loss is going to be 6.4 minus 1.6, which is going to be 4.8 millijoules. As simple as that. Okay, part C. The mass of the aluminium cup is in B is 6.2 grams. The specific heat capacity of aluminium is 910 joules per kilogram per Kelvin. The energy B, Roman 2, is transferred to the cup as thermal energy. Calculate the mean rise in temperature of the cup. There's a change in temperature. So from Q is equal to MC times change in temperature. Then it means because the change in energy is that correspond to that rise in temperature, we shall say 4.8 times 10 power negative 3 should be equal to the mass. The mass is 2.6 grams, so that will be 6.2 grams, that is 6 times 0.2 times 10 power negative 3. Specific capacity is 910 times the change in temperature, delta theta. So I'm pressing the calculator to find delta theta. So when I divide from my calculator, I'm getting 8.5 times 10 power negative 4 Kelvin as the change in temperature. Next, a stiff copper wire XY is held in a uniform magnetic field as shown here. The wire XY has length of 4.7 centimeters as shown and makes an angle of 34 with the magnetic field. So the angle between the conductor and the magnetic field is 34 degrees Celsius. That means the angle normal to the magnetic field will be got from sine. It will be sine. So since we want the force straight away, the force is going to be B sine theta, because we resolve the angle normal to the conductor, or we resolve the angle of the field perpendicular to the conductor. When you resolve this perpendicular to the conductor, this angle is going to be that will be sine theta. Okay, so we now simply just substitute. It is just 2 marks. We just substitute. So this is going to be B. B is 2.6 times 10 power negative 3. Then the current in the conductor, the current is given as 5.4. The length of the conductor is 4.7 times 10 power negative 2 times the sine of the angle, which is 34. Simply press our calculator. So from my calculator, I am getting this as 3.69 times 10 power negative 4, three significant figures in newtons. The current in the wire is now changed to an alternating current. The current in the wire is now changed to an alternating current. Determine the total variation in the force on the wire due to the alternating current. So when the force, remember the force is going to be equal to, the angle is not changing, the force is going to be B sine theta. And we have seen the first force, we have seen the force. So what is going to be changing is going to, B is going to remain a constant. Sorry, B is going to be, of course, because the current is changing, B is remaining a constant, the angle is constant. So I'll simply say that the force is equal to a constant times what is changing is going to be the current. The current is what is going to be changing, because for alternating it is going to be changing. So we have that. I'll just substitute. I'll get two equations. When the force is 3.69 times 10 power negative 4, this was equal to a constant times the value of current, which was 5.4 when it was steady. But now the current in the Y is now changed to an alternating current of root mean square value that. So the maximum force this time, F max, is going to be constant times the maximum current, which I'm calling I naught. And I naught, if we have the root mean square value as that, I naught is going to be the root of 2 times 1.7. So this means F max, the maximum force, is going to be the constant K times root of 2 times 1.7 as the maximum. So if I want to find how the force will vary, I will divide the two equations to find F max. The maximum force F max is going to be equal to, so I'm dividing the two equations. K has cancelled, so this will be root of 2 times 1.7 divided by 5.4, then times 3.69 times 10 power negative 4. I've just divided this equation by that one, and I made F max the subject. Let me check. Root of 2 times 1.7 divided by 5.4 times 3.69 exponent negative 4. So this is giving me the maximum force as being 1.64 times 10 power negative 4 newtons. That is the maximum force. This means the variation is going to be from positive 1.64 times 10 power negative 4 to negative 1.64 times 10 power negative 4. So the difference, or the total variation is going to be 1.64 minus negative 1.64, then times 10 power negative 4, which is like having it as twice. 2 times 1.64 times 10 power negative 4. So the maximum variation is approximately 3.3 times 10 power negative 4 newtons. So the maximum variation is approximately 3.3 times 10 power negative 4 newtons. Okay. A solenoid is connected in series with a battery and a switch. A Hall probe is placed close to one end of the solenoid as illustrated here. The current in the solenoid is switched on. The Hall probe is adjusted in position to give the maximum reading. The current is then switched off. The current in the solenoid is now switched on again. Several seconds later, it is switched off. The Hall probe is not moved. On the figure, sketch a graph to show the variation with time t of the Hall voltage Vh. Of course, we know that the Hall voltage Vh is given by Bi over NTQ. So when there is no current, there is no Vh. When I is 0, Vh is going to be 0. That is obvious. So let's see. The current is switched on here. That means before that there was no current. So there the whole voltage is 0. We draw a horizontal line. So we draw a horizontal line here. When the current was not switched on, we draw a horizontal line. I will increase the thickness to make it visible. So before switching on the current, we have a horizontal line here. And when the current is switched off again, we shall have another horizontal line along the x-axis when the current is switched off. Now, when the current is switched on, there is a magnetic field. When the current is switched on, then there is a magnetic field. So there will be Hall voltage. And the magnetic field is going to be constant. So it means the Hall voltage is also going to be constant when the current becomes constant. but it will take a few microseconds to grow rapidly. So I'll draw some kind of steep line here. I'll draw some kind of steep line here. I don't want to make it perfectly vertical because although it grows very rapidly, so it will not be very perfectly vertical, not be to not be extremely vertical, but it is almost very vertical. It is almost very vertical, but then when the current is on, the whole voltage is constant if the current is constant. So this will be a horizontal line. I've tried my level best to use a ruler to draw a horizontal line. So that is the graph we are talking about. VH is 0 whenever there is no current. VH is constant when the current is constant and not 0. That's why you see VH being like that. These lines, the vertical lines are almost vertical, but they are really not extremely vertical because there is a very tiny time interval for this to change from 0 to maximum or from maximum to 0. That is why you are seeing it a little bit vertical, but almost it's kind of slanting. Okay. Next, the hollow probe is now replaced by a small coil. Now we are removing the hollow probe and putting a small coil. The plane of the coil is parallel to the end of the solenoid. That means now the magnetic field is perpendicular to the plane of the coil because the magnetic field in the plane from the solenoid is coming out horizontally. And if the coil is parallel, the plane of the coil is parallel, it means the magnetic field is normal to the plane of the coil. State Faraday's law of electromagnetic induction. We shall not get tired to state this law. The magnitude of the induced EMF, the magnitude of the induced EMF the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF for the coil is directly proportional to the rate of change of magnetic flux linkage. On the axis, sketch a graph to show the variation with the time t of the EMF E induced in the coil when the current in the solenoid is switched on and then switched off. Of course, before we switch on the current, EMF is 0 because it is off and constant. Constant and 0, EMF is directly proportional to the rate of change of magnetic flux linkage. But now, before we have switched on the current, the EMF, the magnetic field is 0, the EMF is going to be 0. The flux linkage is still 0. So here we have a horizontal line outside. Before switching on the current, we don't have an EMF. We don't have an EMF before switching on the current. When we switch off, the EMF also goes to 0. And also remember, when the current is constant, the EMF is not going to be changing. When the current is constant, the EMF is not going to be changing. And if the EMF does not change, it means again if the current does not change, it means the EMF is also 0. So between the two, when the current is on, again the EMF is 0. But at the process of switching only, at the point of switching only, we shall have a change in magnetic flux. Switching on or switching off, we shall have a change in magnetic flux. This is going to give pulses in opposite direction. Current is switched on, we shall say pulse, a short pulse in an opposite direction. So we shall say short pulse somewhere here. And when the current is switched off, we shall see another short pulse in the opposite direction. So we expect a short pulse here in the opposite direction. So that will be the graph. That will be the graph. When the current is not changing, the EMF is zero because the rate of change of flux linkage is zero. It is constant. Flux linkage is constant, the rate of change is zero. So there is no induced EMF. When there is no current, obviously there is no induced EMF. Not until there is a change. There is only a change in switching on and switching off. In a class, you must have noticed that when the switch is closed, you see a short intense flash which goes off immediately. That's why we have pulses there. And the pulses are in opposite direction because on switching on and switching off, the change is not in the same direction. Okay, next. State what is meant by quantization of charge. This one we have just mentioned it. Quantization of charge means charge exists as multiples of 1.6. So charge exists, charge exists as multiples of 1.6 times 10 power negative 19 coulombs. That is quantization of charge. Or we said charge exists. Charge exists in discrete and equal amounts. In discrete and equal amounts. That's what we mean by quantization of charge. A student carries out an experiment to determine the elementary charge. A charged oil drop is positioned between two horizontal metal plates as shown here. Okay, so that means there are two forces here. Let's see. The plates are separated by a distance 7 millimeters. The lower plate is earthed. It is at negative potential. The field is downwards. Therefore, the potential of the upper plate is gradually increased until the drop is held stationary. So if the drop is to be held stationary, the force due to the magnetic field must be downwards. That one cannot be changed. So the force due to the electric field must be upwards. The force due to the electric field must be upwards. Therefore, this charge must be negative. The charge here must be negative. To experience a force towards high potential, the charge must be negative. Okay? The weight of the oil drop allowing for the upthrust of the air is this. So the weight is given as that. Actually, the value for the charge on the oil drop. The value for the charge on the oil drop. So when there is a balance, the weight, which is the same as mg, should be equal to the force to the electric field, which is q times E, which is the same as q times V over D. So I'm equating the weight to that. So we shall say 4.8 times 10 power negative 14 should be equal to the charge which we want to find times the potential difference is 680 divided by the separation is 7 millimeters. So that is 7 times 10 power negative 3. Okay, we make Q the subject. I will just press my calculator. Cross multiply 4.8 exponent negative 14 times 7 exponent negative 3 divided by 680 divided by 680. So this is giving me Q as 4.9 times 10 power negative 19. 4.9 times 10 power negative 19 coulombs. The student repeats the experiment and determines the following values for the charge on the oil drops. Is getting this one, this one, this one, and that one. Use the values to suggest a value for the elementary charge. So just try to check dividing each of these. Explain your working. So when I try to divide 4.9 by 1.6, I will try to find the common multiple, the common factor here. The highest common factor. Okay, my answer is 1.6 times 10 power negative 19. Of course, I know that, but we can check. All values are approximately multiples of 1.6. That is my explanation. All values are approximately, you can check. All values are approximately multiples of 1.6 times 10 power negative 19 columns. So it should be the elementary charge. Alternatively, it is the common factor. It is a common factor. You can try to check. 1.6 times 10 power negative 19 columns is a common factor. It's a common factor. Okay, next. A hollow probe is placed at distance d from a long straight current carrying wire as illustrated here. Okay, we see a hollow probe. The direct current in the wire is 4.0. Line XY is normal to the wire. The hollow probe is rotated about the line of XY. It is rotated about line XY to a position where VH of the hollow probe is maximum. So at D, VH is maximum at point D because it's rotated to where it is maximum. The hollow probe is now moved away from the wire along the line XY. So it is now taken away from D, where D, remember, VH was maximum. On the axis of the figure, sketch a graph to show the variation of the hole voltage VH with the distance x of the probe from the wire. So we know that VH is equal to BI divided by NTQ. Now I is not changing, NTQ are not changing. What is going to change is B as you move away from the wire, because B, the magnetic flux density, reduces as you move away from the wire of the conductor, or from the conductor carrying current. It increases when you get closer to the wire. Now that we have got a maximum value of VH at point D, and we are now moving the whole probe away, it means B is decreasing. As B decreases, it means VH also decreases. Okay, so that means at D, I will start at D. I will start with a line at I will start with a high hole voltage, and as I move away, the hole voltage decreases. So that means I will draw a curve which will be decreasing in that nature. I want to make it thicker. Let me increase the thickness. So that will be the graph which I'm looking for. The current is decreasing. The current, the curve is going to be of a decreasing gradient, and I'm not sure if it will touch the positive and negative. I don't think it will not go beyond. It will not go in the opposite direction when you move away, because it will change direction to cross the x-axis when you when you come again closer to the wire. But now you're only moving away. The whole probe is only moving away from the position that we had before, so it will not cross the x-axis. And to make it comfortable, the graph line, this curve should be a little bit longer. You can't draw a very short one. That would mean that it would just rapidly be going to zero. Yet they said the hollow probe is now moved away from the wire along the line XY. On the axis, sketch a graph to show the variation of the hollow probe with the distance of the probe from the wire. So the magnetic field decreases gradually as you move away. So it will take some time. And I don't think it would be wise for you to draw a graph which reaches the x-axis. So you just draw a curve tending towards the x-axis. starting from maximum value at D and decreasing. So that will be our graph. Then part B, the hollow probe is now returned to its original position at distance D from the wire. At this point, the magnetic flux density due to the current in the wire is proportional. So B is proportional to current. B is directly proportional to the current. For a direct current of 4.0 in the wire, the reading of the whole voltage is 3.5. Direct current is giving us a reading of 4.5 volts, millivolts. The direct current is now replaced by an alternating current of root mean square 4.0. So we can find the peak in that case. The peak current corresponds to that root mean square. The peak is going to be root 2 times 4.0. And when you press your calculator, no, not 4.0, 3. Okay. The root means since direct current of 4.0 corresponds to direct voltage of 3.5, then root mean square value of 4.0 should correspond to the peak value of root 2 times 3.5 volts. So the peak voltage is going to be 4, that is 4.95 volts. That is the peak voltage. So our graph will range between 4.95 upwards, because the scale here is 0.2 divided by 5, that is 0.4. 4.95 divided by the scale, those are 12, around 13. So this is 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 4.95 is around there. Even at the bottom, 4.95 is around there. 4.95 is around there. Almost 5. Almost 5. So that is around there. Okay. So the period of this alternating current is T. So after every T, we have one complete cycle. After every T, we have one complete cycle. That means all the peaks will go above. They will not stop at 3.5 volts. They will reach approximately 4.9 volts. So I'll just do a reference horizontal line there. They will not go above. They will be above 3.5. They will be around that point. Even at the bottom, the peaks will be around this point here. This is just for reference so that I don't go very far. So we are going to divide one complete cycle into 4 parts. I'll first divide it into 2 to reach half a cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is half a cycle. Then I will divide again this into a quarter. 1, 2, 3, 4, 5. A quarter, another quarter. So if I start from 0, it is going to be maximum at this point here. And it comes back to 0. Then it will be maximum again at this point here. Let me try to increase the thickness. Okay, that's for one cycle. 1, 2, 3, 4, 5 around here. 1, 2, 3, 4, 5. It comes back to 0. Then 1, 2, 3, 4, 5. It comes back to 0. It goes to maximum here. And then 1, 2, 3, 4, 5, it comes back to 0. Again, 1, 2, 3, 4, 5, it goes to maximum. So this is going to be my pattern. As simple as that. What is very important is find the peak voltage. If 3.5 millivolts is corresponding to direct voltage of a direct current of 4.0 amperes, then root mean square value 4.0 will be equivalent to 4.9 volts as peak. So the graph will be at 4.95 volts, or approximately 5 volts as the peak. Approximately 5 volts as the peak. If I've sketched this very wrongly, you can sketch a better one to go up to approximately 5 volts at the peak. Okay. And lastly, for this video, comment on this suggestion. Which suggestion is it? A student suggests that a hole probe in A is replaced with a small coil connected in series with a multivoltmeter. Constant current in the wire is 4.0 amperes. In order to obtain data to plot a graph showing the variation with distance x of the magnetic flux density, the student suggests that readings of the millivoltmeter are taken when the coil is held in position at different values of x. Held in position at different values of x. The student suggests that the hole probe is replaced with a small coil connected in series with a millivoltmeter. We are replacing a hole probe with a coil with a millivoltmeter, and that means it is going to be relying on induced EMF. Then the student is saying there is a constant current in the wire that we have seen. In order to obtain data to plot a graph, the variation with distance x of the magnetic flux density, the student suggests that the readings of the millivoltmeter are taken when the coil is held in position. Comment on this suggestion. I don't think that suggestion will work. When the coil is held in position, then the induced EMF is going to be 0. And if the induced EMF is 0, then what readings of the millivoltmeter will you get? So we are saying the EMF, since there are two marks, the EMF is induced. The EMF is induced. EMF is induced in the coil when the magnetic field or flux is cut or is changing. EMF is induced in the coil when the magnetic field or flux is changing. So if we holding the coil at one position or holding at each position, means that the magnetic field does not change. The magnetic field does not vary or does not change. So no EMF is induced. No EMF is induced in the coil. So there will be no reading. So no reading in the millivoltmeter. However, we can give this student a suggestion. As physics students, we know that EMF is induced in the coil when the magnetic field or flux is changing. But holding at each position means the magnetic field does not change or does not vary. So no EMF is induced in the coil. So no reading in the millivoltmeter is going to be observed. However, we can now give the student another suggestion. If we want a reading at each position, switch off the current and take a millivoltmeter reading. That is another suggestion. So we could say, oh, switch off instead, switch off instead, switch instead at each position, switch off, switch off the current, switch off the current and take the millivoltmeter reading. That is one. Another student somebody else could suggest that, okay, at each position, hold the coil at each position and then rapidly remove the coil from the field and take the meter reading. That one is very possible. You can say hold, instead hold, or another alternative you would say instead at each position, rapidly remove the coil. Rapidly remove the coil from the field and take the reading. So these will be the better ways of obtaining the values, other than holding the coil in one position to not give any reading. But you can hold it in one position and then rapidly remove it, or you hold it in one position and then switch off the current and take the millivoltmeter reading, because there will be only an EMF induced when the current is switched on or switched off, or when the coil is moved away rapidly, you will notice the reading. Okay, so that is the end of part 2. See you in part 3, and I hope you have enjoyed this. See you. Bye bye.